Good morning, everyone. I request the participants to mute your mic.
Swati, can you hear me?
Yes, sir. I can hear you.
Professor Arak has joined.
Yes, sir. He has just joined. Sir, actually, you're host now. Can you make Kalapriya host so that she can take over? Okay. Can we begin, sir?
Yes, you can begin. And you can inform Professor Arak that he need not worry about the admit button.
Okay, sir. Professor Arot, can we begin, sir? Okay. Greetings from NITT Optica and SPICE student chapter. As Sir Isaac Newton said, what we know is a drop. What we don't know is an ocean. I, Swati Shaktivel, President of NITT Optica Student Chapter, am extremely happy to welcome you all to the day 2 of this International Symposium FIFA 21. I deem it as a privilege and to welcome our speakers, Professor Anthony S. Arot, Professor John Philip, Professor Ishwar Bacham Reddy, our enthusiastic participants, Student Chapter Staff Advisor Professor B. Sashti Kumar, Technical Advisor Dr. Justin Josephus, other faculty members and organizers. I'm sure day 1 served our participants up with interesting lectures and some serious knowledge and motivation from Nobel laureate Professor David Vineland, Professor Dinesh Kumar Srivatsava, Professor Murugeshan Badake Madam, and of course, Dr. Barbara's interview was very enlightening and insightful too. Along the same line, I would like to present today's session with a great enthusiasm, and to begin with, I take privilege and honor to introduce our premier speaker, Professor Anthony S. Arot, Professor Emeritus, Simon Fraser University, Canada. Professor Arot is a nonagenarian and a legendary physicist who has made innumerable contributions in the field of magnetism. He invented a famous method known as the Arrowt plot in 1957, which is being widely used even to this date to determine the Curie temperature and nature of magnetic transition in ferromagnetic systems. He has developed remarkable theories on liquid crystals and has played a central role in designing, construction, and operation of thermal neutron facility at the Triumph Particle Accelerator, Canada. He has worked with several leading institutes. He has worked with several leading institutes and research laboratories across the globe, like Brookhaven National Laboratory, University of Michigan, ETH Zurich, Switzerland, Weizmann Institute of Science, Israel, University of Tokyo, Japan, and the list goes on. All his life, he has been bestowed with quite a few prestigious awards and fellowships, of which Alice Chalmers Fellowship in Magnetism, Guggenheim Fellowship in Physics, Japanese Society for the Promotion of Science Fellowship, Simon Fraser University Research Fellowship are the highlights. The Science Council of British Columbia has endowed Professor Arrowt with the Medal of Achievement in Physical Sciences, and the Canadian Association of Physics honored him with the Medal for Lifetime Achievement in Physics. Professor Arrowt was featured in a documentary named Portrait last year, where he continues his research in the field of magnetism while being surrounded by hundreds of portraits drawn by his late wife, Patricia Graham Arrowt. I can bet that this documentary is a reflection of his real life. He shows compelling research interest and knowledge dissemination at the age of 93 and a half, cause of which he agreed to our invitation by the drop of a hat. Now, I gladly welcome Professor Arrowt to take the stage and present on Why Can I Fit the Data? A question without an answer. Over to you, Professor. Professor Arrowt.
Can you hear me now?
Yes, Professor, I can.
Now, what do I have to do next?
Share your slides, Professor, please.
Do what?
Please share your slide. Share your screen.
Share screen.
Yes.
Okay, hit share screen. Okay, and now there's my talk. Okay, I click on the talk.
Yes.
Let's see if anything happens. Oh, click on the window application you want to share. Okay. There it is.
Yes, yeah,
I got
it is starting
I
to
just have to pull it up. I have to pull it up from the bottom here. Okay.
Sir, you
What do
may
I-
also start the video, sir.
Now what do I do?
Sir, you can switch on your video. You can start your video if you wish.
I can start my video. Okay.
Yes.
Slideshow. From current slide. Okay. Now, can you see the slide and you can hear me?
Yes, sir. We can see the slide, but we can't see you.
You don't have to, wait, you can
Okay.
only see the slide, yeah.
Yeah, okay, that's fine.
Well, how do you see me? What do I do to see me?
Sir, adjacent to the mic button, there's a video camera button. You have to click that.
Oh, start video. I didn't
Yes,
click
yes.
start video. Here we go. There I am. I'm
Yeah,
up in the
we can-
corner. Okay. I'm up in the corner and I have the screen. Can I start the talk?
Yes, sir. I'll sign off. You can.
Okay. So I can click on here. I don't know why. Okay. Uh-oh. How do I move that above? I got a problem here
You
because
have to click your left arrow, Professor,
oh, boy.
in your keyboard.
Okay. The talk
Yes.
3. Okay. I have trouble that the thing at the top still stays there. Okay. But what do you see? Do you see my full picture, or do you see where it says stop share screen and all that?
No, sir. We see only your slide.
Oh, okay.
Okay,
We're all
that
right.
will be visible only to you. We see only your
Okay.
slide. Yeah.
Okay. All right. A vacuum flask, also known as a Dewar flask, Dewar bottle or thermos, is an insulating storage vessel that greatly lengthens the time over which its contents remain hotter or cooler than the flask surrounding. It invented by Sir James Dewar in 1892, and that's a picture of him there. The vacuum flask consists of two flasks placed one inside the other, and you can see that in front of him, and joined at the neck. The gap between the two flasks is partially evacuated of air, creating a near vacuum, which significantly reduces heat transfer by conduction or convection. Vacuum flasks are used domestically to keep beverages hot or cold for extended periods of time and for many purposes in industry. This talk is about energy and information. It's been claimed that the thermos bottle is the greatest invention. It keeps hot things hot and cold things cold, and nobody knows how does it know. I'm an experimentalist. Oh, darn, that's I can't see that. Okay, I got to go back. Sometimes my laboratory is my computer. I work at a corporation, a university, a car company, or a government facility. In the 1970s, I used government funds at a national laboratory at a university across town from the university that employed me. I was at Simon Fraser University. Triumph is at the University of British Columbia. Triumph stands for Tri-University Meson Facility. This 56-foot diameter accelerator is the largest cyclotron of its kind. It's a source of medium energy protons. Triumph produces internal beams of negatively charged hydrogen ions, which is one proton with two electrons from an ion source. The ions are transported through an evacuated electrostatic beam containing elements to focus and steer the beam over 60 meters to the cyclotron. The 520 MeV variable energy cyclotron accelerates those ions with a high frequency alternating electric field and uses massive 6-sector magnet to confine the beam in an outward spiral trajectory. Inserting a very thin graphite extraction foil strip removes the electrons from the hydrogen minus ion while allowing the proton to pass through. The proton, because it's a poly, I have a problem because things keep coming on the scene. Now, how do I make my screen smaller? Is what I got to figure out. I got to make my screen smaller, and I don't know how to do that. Oh boy.
I'm sorry, Professor. You want to make your screen smaller?
Yeah.
Professor,
want to make
you minimize the screen.
Yeah.
Okay, your video, you mean? Sir, there'll be a small...
Let me do control minus, see if that does that. Now I got the whole talk there. That made the screen smaller. Let me go back to here. I have this problem. I'm not going to be able to see the words. Well, we'll just have to live with it. My laboratory is my computer sometimes. Okay, I got that far. Now let me go further. I'm talking about beamline 1, and there are 2 targets on beamline. And the second target is the muon spin resonance target. It's a powerful probe into materials like semiconductors, magnets, and superconductors. Beams of positive muons are created with their spins lined up in the same direction. When these beams are shot into a material, the muon spins precess around the local magnetic fields in the material. The unstable muons soon decay into positrons. Since these anti-electrons tend to be emitted in the direction of the muon spin, USR scientists can examine how the internal magnetic fields of different materials. Is it all right? Can you hear me?
Yes, sir, it is. Other participants, please mute your mic. Thank you. You can continue, Professor.
What do I have to do?
You can continue, Professor. There is no issue.
Is everything all right?
Yes. You can continue, Professor. It's all right.
There it is. Are we all right now?
Yes, Professor.
Oh, okay. Thank you. Oh, boy. Okay. Okay. There's downstream of T2, there's a 500 MeV facility, which is used to produce strontium isotopes for medical imaging generators, as well as providing the proton source for the thermal neutron facility. The extension of beamline 1A from T2 and the construction of the thermal neutron facility was my personal responsibility. I lived in Fisherman's Cove and I traveled 100 kilometers a day. Uh-oh. Uh-oh. Now, why didn't it didn't, no, there we go. Okay. There I am traveling 100 kilometers a day. I lived over here and I had to go over to Simon Fraser and then back to Triumph here and then back through Vancouver, back to Horseshoe Bay every day. I had time to think, and believe me, that's dangerous while driving. You really shouldn't think while you're driving. You should think about driving, not about anything else. One of the things I had to think about was capturing the muons in a target with a collimator and designing the beamline that transported them to the thermal neutron facility. When I designed the collimator for the proton beam, I had to know what happened to each of the protons that entered the sides of the iron collimator, rattled around until they left the iron and rejoined the beam. I guessed an equation, which months later I presented at a progress review. A veteran of the cyclotron community asked me what was different than what Rossi had done at Los Alamos during the war. Well, I did not know about Rossi, so I read his description of how he wrote down the differential equations for the diffusion of protons. The solution to a differential equation comes from guessing the answer. That's how it's done. Rossi showed the equation to Fermi, who suggested he try the very same function I had guessed without knowing the differential equations. The question is, how did I know? I had to think about designing the beam transport system, which would take the beam from the meson, from the T2 to the thermal neutron facility. A beam of charged particles is transferred by using magnetic fields for alternating the focusing in the X and Y plane when traveling in the Z plane. I did the calculations using the first handheld calculator created by Hewlett-Packard. The HP65 read programs from a magnetic strip that allowed 100 program lines. Some of the most efficient programming ever done was done by HP mathematicians constrained to just 100 steps. My calculations were checked later by the beamline designers who knew better than to trusting an amateur. An important scientist, David Parnas, once said, as a rule, software systems do not work well until they have been used and have failed repeatedly in real applications. David Parnas predicted that Reagan's Star Wars defense would not work because it would have to work the first time. And that's led to him leaving the US and coming to Canada. I had to think about designing the target and thermalizing the protons, turning the protons into neutrons. Protons are converted into neutrons in a target of lead. This is to avoid creating transuranic isotopes or polonium, which itself is a very bad system. So I didn't want any transuranic elements. I didn't want any polonium in the city of Vancouver. The heat is extracted through the walls of a steel cylinder immersed in water at room temperature. The temperature of the lead is just above its 327 Celsius melting point. The lead convects heat to the inner wall of the steel container. The amount of heat that flows into the water must be below 300 watts per square centimeter, or else you get what's called burnout. If the thickness of the wall is made greater than 1 centimeter, then the heat flow has to be less than 300 watts per square centimeter, because the temperature of the water is known and the temperature of the lead is known. If the thickness of the wall is greater than 1 centimeter, the heat flow is less than this, and the formation of a vapor barrier is avoided. As this design of the beam dump had not been used before, the regulatory agency said that it must be tested at full power. Wait, I got an idea. Let me just see if I can get back out of this. Let me do this. No, yeah. If I do this, I can see, you can still see my screen, and I can see the whole thing now. I figured out what to do. I made it smaller. Okay. Now I also have right here. Okay. As the design of this beam has not been used before, the nuclear regulatory organization said it must be tested at full power before there was any time for a significant buildup of harmful isotopes. This was done, and it did work the first time. One of the safety engineers had insisted that a pipe be attached to the top of the horizontal cylinder to monitor the integrity of the system. The pipe would contain all the gaseous isotopes produced by spallation. All possible gaseous isotopes were considered, but it was neglected that mercury at 327 is a gas. When the temperature got safely to 327, the beam was switched off and success was toasted. This was the first big beam was taken out of Triumph, and the beam dump had worked perfectly. Well, yes, but that's when the siren on the detector monitoring the pipe went off. Every proton that hit the lead created an isotope of mercury, and some of those were radioactive. And so what I had to do was capture all the mercury before it reached the monitor. The molten lead neutron source has now run for 48 years, is now part of what's called the neutron irradiation facility. Mathematics had little to do with this because convection is too difficult to describe. Now, I think I have to click over here to get to the next page. There we go. I had to think about slowing the neutrons down to energies used in neutron diffraction. They are still high energy. I thermalized the high energy neutrons by capturing them in heavy water. I extracted a 100 centimeter squared beam of thermal neutrons, which were monochromated by reflection from 2 stacks of silicon crystals, one 3 meters above the other. The beam, you can see the picture over here where you see the beam comes into here. This is where the lead target is. Below the lead target, this beam looks below the lead target into the D2O tank, and then comes out here. And then I had a stack of crystals in this corner right here, which reflected the neutrons up to the top, and then they get reflected again and came back out along this path here. And this was the path that the neutrons took to my diffractometer, which was up on the shelf. So for 15 years, I was the only one who had his own personal neutron diffraction facility. The spectrometer was run by computer over a telephone line. And that was only possible in 1980. It wasn't before that possible to do that. When the computer failed, I would call the control room at Triumph and ask the operator to go to the thermal neutron facility to push the reset button. Now, what was necessary was to slow down the neutrons. For that, there are many mathematical programs that have developed to describe the slowing down of neutrons in water, because that's where all of this stuff starts. Now, where am I here? I have to scroll this down here. Okay, here we go. I had time to think about maintenance, but that's where I failed. After 15 years, one of the welds on the aluminum tank containing the D2O caused tritium to enter the Triumph common vacuum system, and the alarms went off everywhere. The D2O was found to contain nitrous oxide, which at low concentration attacks aluminum. The design of the thermal neutron facility called for a blanket of helium gas to separate the D2O from the atmosphere. This part of the routine maintenance became neglected, and I lost the use of my neutron spectrometer. The TNF survived as a present-day neutron irradiation facility, which allows me to have this nice graphics, which you see over on the right, was not available at the time that I originally did all this. That's typical of what everybody does today with graphics and thinks nothing of it. But that development of graphics has been taking place since 1980, and I'm proud to say one of the major players in the development of scientific visualization was my son Matthew, who carried this out at the Center for Supercomputing Applications at the University of Illinois, where he did almost everything for the first time in computer graphics. He also worked for DreamWorks at one time, and he's I'm very proud of my son who does all that. But despite the fact that I lost the facility, I did have those years where I could carry out experiments important to understanding the diffraction of curved crystals. I had a very low intensity beam, but it was a big beam. And if I was using a big target like a silicon wafer, I had very good count rates. But I had this available half of every year because that's how much fraction of the time that the cyclotron ran. And I used that to solve problems that no one else did because I had the time to do it. I had time to think about how to bend silicon wafers to monochromate and direct thermal neutron beams. I studied hundreds of silicon wafers that I elastically distorted. I showed that the center of the mosaic distribution varies linearly with distance across the silicon wafer. The mosaic distribution is a series of little blocks. When you have a single crystal of silicon, it's not a perfect single crystal, but it's blocks of very narrowly defined crystals. But because the mosaic varies as you go across the way, it's as if it were ever curved, because that's what would happen if you curve the crystal. You're bending where the center of the mosaic is everywhere. But the fact that crystals behave that way was a mystery that was ignored for 60 years by people who studied photons and electrons and particles by diffraction. You could take a wafer and put it on your spectrometer and look and see an intensity, rotate the wafer, which is a thin crystal, around by 180 degrees, which shouldn't make any difference whatsoever, but it did. And people just shrugged their shoulders because there was no possible explanation for this. Well, I was able to figure out that it came about because of the fact you had a mosaic distribution which varied linearly across the silicon wafer. An international workshop on bent crystal monochromes was held 10 years later, and these are now in common use all over the world. If you type in bent crystal monochromator, you'll get lots of responses. Mathematics describes this whole thing without any difficulty at all. Now, where am I here? I have to make sure I click on the right one. My work lives on, though, even though the thermal neutron facility no longer gives you thermal neutrons. It does provide irradiation, which is used for a lot of studies. And there's a picture of the neutron irradiation facility, and these beam lines, which you see right here and right there, are my original beam lines, which were used for neutrons, are now used again, but now for high energy neutrons that go through that way. Let's see, I have to click here. In 1965, while at the Ford Motor Company, I established a neutron diffraction facility at the University of Michigan. My first experiment was to check the scattering of the spin density wave antiferromagnetism from a nearly perfect crystal of chromium. I got the crystal of chromium by pure luck. And this, one of the most important things about physics is that it's better to be lucky than smart. I found though the harder you work, the luckier you get. But I got very lucky. I ordered some chromium, which I was used to make an alloy. And chromium is made by what's called an iodide process, in which they deposit the chromium is evaporated at about 1400 degrees Celsius, and it condenses on a quote cold finger at 1100 degrees Celsius. And the crystallites grow on this so-called cold finger. And that's how you get a very pure chromium. But this, you take the conglomerate of all kinds of crystals which grow on this cold finger, and you send that off as pure chromium to be used for whatever everyone wants to use pure chromium on. But these are packed by women who, when they go look at the chromium, they see that they're beautiful little crystals sometimes, and they pick them out. They use them for earrings and jewelry. And I found out later that in the chromium that I ordered, there was this near perfect single crystal of chromium, which the women had missed. And that was extremely important because it changed our understanding of chromium. I'd seen the results of others, which seemed wrong to me. They didn't fit the mathematical description I already used for what a spin density wave onset should look like when you have a second order phase change, which it was assumed to be. I took this perfect crystal, put it on a pedestal on my diffractometer, and I heated it with a hairdryer with a mercury and glass thermometer behind the sample. It was a very crude experiment, but I could do it quickly. The thermometer read 100 degrees Fahrenheit. The thermometer was from Fahrenheit, which is still below the reported transition temperature for the disappearance of spin density wave. I was watching the count rate on the helium detectors when they stopped counting. I went out of the diffraction room, which used wood for shielding from the neutron background, and that's why I had to leave there to be able to see that the reactor had not shut down. Well, the lights for the reactor were still on, so it had not shut down. I had discovered that the magnetic phase change in chromium was not second order change that had been assumed. The second order change was interrupted by a first order change. This was an unknown property of an extremely well-known element. The theorists then showed that by symmetry, it had to be first order, but nobody predicted that. Chromium is unique among all the metals in that the magnetic transition from a paramagnetic high temperature phase to an antiferromagnetic low temperature phase takes place at the Néel temperature, which is approximately body temperature. In thermodynamics, there's a critical temperature Tc for the onset of a second order phase change. In a gas, it's where droplets first appear on cooling from high temperature. I think you've all seen the phase diagram for a liquid, and there's the critical point. And over here, it's a liquid, and here's a gas. If you go from liquid to gas, you know you're going from liquid to gas, but you can go all the way from liquid all the way around to the gas if you go above the critical point and never see any real difference. These are connected this way, but there's a critical point in which you get this place where you have evaporation between the liquid and the gas. In ferromagnetism, there's a Tc, which is where on cooling from a high temperature, regions of ordered atomic magnetic moments occur over distances large compared to the atom spacing. This critical temperature in ferromagnetism is called the Curie temperature, and here's Pierre Curie, who gave his name to this, and he was married to Madame Curie. Before the chromium discovery, I was most known for the criterion for the onset of ferromagnetism from the dependence of magnetization on the applied field. It's used to determine the Curie temperature, TC. In 1995, I said that the field divided by the magnetization is T minus the critical field divided by a characteristic temperature, T0, plus the magnetization divided by a characteristic magnetization, M1, raised to the second power. And this used three parameters to fit the data. And this became a very popular way of finding out where the Curie temperature was. In 1967, I replaced this by a slightly different formula in which I raised H over M to the power of 1 over gamma, where gamma was a non-integer. And I replaced the squared on M over M1 by 1 over beta, which is again a fraction. And this used 5 parameters. There were 12 years of intense study of the first version in which no one else came up with a modified plot. In other words, I went from the 1955 to 1967 with thousands of people all over the world using this, but no one made the change. During that time, Ken Wilson got the Nobel Prize for explaining why you should have non-integer exponents. Every new magnetic material is characterized by the parameters in what is often called the Arrett-Noakes plot. This activity is driven by the needs for magnetic refrigeration. Different exponents are interpreted as reflecting different mathematical models of ferromagnetism. The integer exponents used in the original Arrett plots correspond to models where the exchange interaction, the interaction which is lining up the spins, extends to all pairs of atoms, not to just the neighbor, a few neighbors. There are over 250 papers a year report new ferromagnetic materials, and all of these use Arrett plots to interpret the results and detect anomalous behavior, which they can use for rapid communications. So they're always looking for what people call the funnies, things that don't behave as they are expected to behave, and then you know you've discovered something. The non-integer exponents were explained using renormalization group theory. And this is for what Ken Wilson got the Nobel Prize. The expression for the modified Arrett plot is reported to be a rigorous expansion of renormalization group about the critical temperature for the onset of ferromagnetism. But my understanding of this is not sufficient for me to communicate, to make commentary. And by the way, there are full books written on this subject, but you don't have to understand something to use it. In this case, the first term in the expansion is sufficient to fit the data. The rest is to satisfy the theorist. Now, I use micromagnetics, and micromagnetics describes the patterns of ferromagnetism at temperatures that are so far below the Curie temperature that the changes in temperature do not change the patterns. So that instead of the phase change being driven by temperature, though, the phase change in magnetism in micromags are driven by B and H in Maxwell's equations, which cause the directions of magnetization to change with position and create new patterns. The field is from an external source, H0, that acts on the finite size ferromagnetic bodies, which I have on my computer, that leads to a second order phase changes in the magnetic patterns, including the often transition from a flower to swirl state. The flower swirl state is shown over here on the right. This is a flower state cross section, and as the transition goes, the center of the pattern moves to the right at the top and to the left on the bottom, and that's a magnetic phase change. And it's actually second order phase change which is getting there. And this transition from the flower state is something which is universal in magnetism, and it's what I'm trying to study. To do that, I need a source of the field. And the source of the field which I used on the computer, it's not a real source, it's on the computer, but it's still a coil of wire, and it has a low resistance, which is sufficiently that there's no heating, and the current is not in any way influenced by the presence of magnetic fields. In the real case, you would have those effects. The coil is called a solenoid. The solenoid and the iron at zero temperature are on my computer. They are defect-free. The sample I study here is a cube, 24 nanometers by 24 nanometers by 24 nanometers, with voxels, which are 1 nanometer by 1 nanometer by 1 nanometer. On the computer, I can see what the magnetic unit vector is doing at every iteration of the calculation at each of the 13,000 voxels and values of each of the terms in the energy. There's nothing equivalent to that in the real world. The picture on the right I didn't mention was is from a book called Spintronics Handbook in chapter 3. And I got to write the chapter twice, as there have been 2 editions a decade apart. So I've been able to summarize things that I knew and put them into a book twice in the last 10 years. The field for solenoid is used to study this transition in the simplest of case. Using a small cube of ferromantic iron at zero temperature, there are only the flower states when the field is from the solenoid, when the field from the solenoid is along the Z direction and large in either direction. You get only then the flower states. But below the critical field, below a critical field, which for a 24 nanometer cube is 453.2896 Ersteds, approximately, the swirl states are lower energy than the flower state. At HC, the energies are the same. By the use of fields from a current along the Z axis, a swirl state can be created in the critical field. You can be in the critical field, and then you can apply a current along the Z axis, and that current will rotate your spins and create a swirl state. When the field from the current is removed, the relaxation of the swirl state takes a very long time, so long that we can only describe the beginning of the process, and by analysis conclude that the swirl state would eventually become a flower state. Eventually is almost forever. We start with a configuration where the magnetization is fully aligned in the critical field and watch it decay. It quickly goes to the flower state and main state all the way to the limits of double precision calculation, and this is an exponential decay. The swirl state, though, exhibits critical slowing down, and the flower state does not. Relaxation in the flower state has the exponential time dependence. The relaxation in the swirl state follows the inverse of time. These statements are powerful in their simplicity and accuracy. The relaxation process involves the transmission of energy and information. In the flower configuration, every voxel is doing something different. In the swirl state, it takes many iterations for the far voxels to exert their influence on the voxels on the distance away. And that's what it's about. It's about the transmission of energy and information. And none of this is published yet. I've put some of this out here, but you guys are getting to hear this for the first time. A second order phase change occurs between 2 patterns of magnetization that are closely related. The second order change in pattern that is the focus of this work is being the pattern called the flower state and the one of the patterns called the swirl state. The swirl state has a hand in this. So there are transitions between the flower state in either the clockwise swirl or the counterclockwise swirl state. The transition between a clockwise swirl state and a counterclockwise swirl state is through the flower state itself. You have just a rotation of the spins from one way to the other takes you through the flower state to the other configuration. Finding the time dependence of these configurations during such a transition was the goal of this work, particularly when that transition occurs at the critical 8-0, where a critical field, where the translation takes forever. This is called critical slowing down. The time dependence of a particular property P, whatever it is, at T equal T critical is found to be the inverse of the time. These thoughts are expressed in a draft paper in progress. This leads directly to the question, why is mathematics so successfully in modeling the universe we habit? This is an often asked question and never fully answered. This work is about searches for understanding centered on the simplest of the three-dimensional magnetic structures, the flower and the swirl states, which allow, there's no ambiguity what we're looking at, even though there are flaws in computer simulations from truncation and round off. This cube of iron is essentially defect-free. We have intentionally put single voxel bifurcations into the calculation and to show that their effects die out with time and do not disturb the relaxation process. In other words, you can go in there and make a computer mistake, and the computer mistake will heal itself. This indicates the dependence on reverse time may well show up in real systems and not only in magnetism, possibly requiring just large numbers of elements with diffusive interactions in order for this new rule of physics to be applied elsewhere in the universe. This is the abstract of I have written an abstract on the subject, and this is my co-authors, Terry Templeman, who's worked with me for 40 years, and he's essentially been my bookkeeper and kept me honest. All those calculations which I talked about on the designing the reactor were done with Terry working with me, and all of my computer calculations come from the work of Michael Scheinfein, who I've worked with for 30 years. It's his code that I'm using for these. The abstract says the micromagnetics of a cube of iron, 24 nanometers on the edges, is shown to demonstrate a time dependence of the energy terms proportional to 1/T at the critical field for the second order transformation from the swirl state to the flower state. This simple law emerges from a complex system of nonlinear integral differential equations called LLG, which are solved and analyzed with full double precision using the 41,000 components of the unit vector magnetization M in the 13,000 voxels, each one of which is a 1 nanometer cube. So there's the voxel, and there's the unit vector magnetization. All I can do is rotate in there, and there's these are all the voxels which you see over here. Now, here's a cross section of the flower configuration on the bottom slice of this cube. And as you can look over in the corner, you can see that this is a flower state, that these guys all are pointing in towards the center. Everywhere you look, people are pointing in towards the center. And that's called the flower. This is the clockwise swirl. Picture look pretty much the same. Yeah, if you go back, you take a quick look here. This is where we were. This is where we are now. But if you look down in the corner, you can see that this cone is not lined with the one in front of it. He's rotated clockwise. And this there is therefore what the clockwise swirl looks like. Now to come over here. Here are the two configurations. They are different, as we've said before. Just look carefully at the corner down here. This right here does not point to the center of that one. This guy does point to the center of the guy ahead of him. The dynamic equations which describe all this follow from the rate of change of magnetization respect to time is equal to the gyromagnetic ratio times the magnetization, unit vector magnetization, this is, cross the H effective. H effective is the sum of all the fields at work. There's the field H0 is what comes from the solenoid. Then you have the other fields are effective fields, and they come from derivatives of the energy with respect to the magnetization. One of them is called the exchange energy, which is responsible for lining up all the spins. The anisotropy energy is the fact that in a crystal, certain directions are preferred. In a cube of iron, the preferred direction is along the edges of the cube, parallel to the edge of the cube. The magnetostatic energy is gotten by having to sum over all of the spins of the system. It's an integral over the volume of the cube. In addition to these energies, there is a term coming from the friction. There is a dissipation here. For this to relax, there is a dissipation, and alpha is called the Gilbert damping parameter, which appears in these equations, which are called the equations of Landau and Lifshitz. And that's where the word LLG comes from, Landau, Lifshitz, Gilbert. The magnetostatic energies are integrals over the volume of the cube. You have to take every spin and interact is interaction with every other spin. That's essentially a double integral over the whole system. And how you have to handle that is part of the problem. The exchange energy is actually just given by the angle between two adjacent spins. It can be written as the sum of the squares of the first derivatives of each of the 9 components with respect to each of the 3 components with respect to each of the 3 directions, which gives you 9 terms that have to be squared to get the exchange energy. But the exchange energy can also be written as Laplacian of M, which is quite unusual because the exchange energy was always written before with the 9 terms as a first derivative squared. And what I showed was that you could do it because it's a unit vector has unique properties that allow you to replace the sum of the squares of the first derivatives by the second derivative. It's because of the fact there's a rotation involved. And the vector Laplacian is shown on the far over here on the right. This del squared is the vector Laplacian, and it's the gradient of the divergence minus the curl of the vector. And that is something you can actually think about because the mind can envision curls and divergences. The other thing that happens in all this is that the dMdT, the rate of change of magnetization of time, appears twice in the equations because the equation starts with dMdT and H effective has a dMdT in it from the term, which is alpha. Where's the term? We lost it. Here it is, alpha mdt right here. You can see that term. That appears on both sides. So the result is that the damping goes as alpha over 1 plus alpha squared. And so that's the damping coefficient. The anisotropy energy is cubic and it's aligned with the cube edges. The equations are solved using the predictor-corrector methods of Hamming. Hamming is my hero in the world of magnetization of computers. Hamming is the guy who's responsible for computers being able to work because he figured out how to correct for the errors that computers will always make in thinking. You could the Hamming code is just essential to the Hamming correctors are absolutely essential to making computers work. The code, the Hamming code is in the LLG microcomputer simulator written by my friend Mike Scheinfein that has been used now for decades. The initial condition for the computer experiment is to start with all the magnetizations in every voxel aligned up into the critical field, or a field very close to the critical field. The relaxation in the flower state occurs rapidly as there is no need to transmit information throughout chains of voxels. We apply a current IZ through the cube, rotating the magnetization clockwise or counterclockwise, depending on the sign of the current. After the full relaxation of the fields in that current, those fields are turned off, which leads quickly, because it's already in what looks like a curl state. Now this is no longer a driven curl state. This is the curl state without a current because we took the current off. As the time dependencies are weak in the swirl state near critical, they are followed for millions of iterations to facilitate the analysis. The time dependence of the demagnetizing energy, that's the interaction of the dipole-dipole interactions between all the moments, decreases to drive the swirl, and the exchange energy opposes and almost cancels the change in the demagnetizing energy. It's minimizing the magnetization energy that makes the swirl appear, it can be fitted, as I've shown here, to 1 over T. the 1 over T. This is a 1 over T fit. One is for the exchange energy and one is for the demagnetizing energy. The exchange energy is coming down. The demagnetizing energy is going up with time. The exchange energy is going up. I'm sorry, I got this wrong. How did this that way? The demagnetizing energy is coming down with time. No, that's the exchange energy coming down with it. What's wrong with me? The exchange energy, oh, this is the relaxation process. Yes, yeah. We originally got the exchange energy by putting the current on, and now I'm taking the field from the current off, and the exchange energy then is relaxing, and it goes down as it relaxes, and the demagnetizing energy goes back to where it was. It's increasing, and the fit line is the green curve, which is over the data line, which are the little dots underneath the curve. It's as good as you can get. These are just fantastic fits. If you ask what is this exponent, which appears here as a 1, when we say it's 1 over time, I can allow the computer to say what it thinks the exponent is. So I can make that a variable, and the kaleidograph program, which is doing the calculation, will try to find out the best value for 1, and the best value for 1 turns out to be 1.0003 or something like that. So it's to very great accuracy that they want, and that's despite the fact that it has all these parameters to play with in doing the fit. Here's the same fit, which I'm doing now for the anisotropy energy. And again, you can see that underneath the red curve, which is the fitting curve, are the little black dots, which represent the actual values. And if you look here, you see, if you ask, how well do I know M1? Well, I know M1 to 1 part in 10 to the 6th. M2, I know to 1 part in 10 to the 8, I guess. And so these numbers are extremely well known. There's nothing else in the world that you can know this accurately. This is a sandbox for people who want to really find out what's going on. The confidence in results of the LG calculations come from decades of running the program. This analysis comes from a program which has been used for 3 decades called Kaleidograph. The program asks for a function with parameters to be fit and asks for initial guesses for each. For Kaleidograph to work correctly, the guesses have to be close to the final answer. So if you use Kaleidograph, you spend your life guessing at what to tell, how to Kaleidograph to tell to start to do the fit. So you have to guess the answers in order to get it working correctly. If the guesses are too far off, the program will fail, but not always. The program can sometimes find parameters fit the data in very unexpected ways. I don't want to go into that right now, but it is quite amusing what Kaleidograph can come up with. Here are the cones. What else do we have here? Okay. The variable which I'm using here is tau. That's T minus T1 divided by T0. It's the measure of time is scaled by this number T0. That's what's the scale. And you can see that when T is equal to T1 plus T0, tau is equal to 1. When T is equal to T1 plus 2 times T0, tau is 2. And when T is equal to T1 plus 3 times T0, tau is 3. If we let P be a property that's being measured as tau increases, for instance, in energy, P generally decays with time, but when the changes are at the limit of the precision of the calculation, subject to truncation and round off, P can oscillate in what are called Poincare cycles or just plain stop calculating. If I set P equal to P0 times this function, FC of tau, where the function is, I want to find that function at the condition of criticality. That's what we're trying to do to describe critical slowing down. And I worked on this for 5 years. The answer is not exponential. The answer is 1 over T, and that's what this is all about here. Works as 1 over T. If you're doing an energy, if it's doing a component of the of the magnetization, it's the square root of tau. And if I'm looking at the time derivative of the magnetization, it's the 3/2 power of time. In fact, this is where I was looking at the time derivative of the magnetization when I discovered the 3/2 power law from which these other power laws follow. The critical field HC is where T equal to T0, T minus T1 for all the energies forever. For all other fields near TC, if one waits long enough, it will eventually become an exponential. What starts out as this 1/T law eventually becomes exponential on the tail if you wait long enough. But if you're at the critical point, no matter how long you would wait, it would still look like 1/T, and we would never get to the exponential. And that's the story, I think. In no ways, I got one more. Oh, these are just showing more of these curves and showing how good it is. I think this is probably the time to stop and see if I can do anything with questions. I don't know whether I can do anything with questions, but I'm willing to try. And you're probably going to have to give me some help because I'm deaf and it's very hard for me to hear. So, Swati, what do I do now?
Thank you, Professor, for your presentation. Participants, please post your questions in the chat box. In the meantime, Professor, I have a question for myself.
Go ahead, please.
Okay, so the Arrowhead plot, you have described Arrowhead plot for ferromagnetic transitions, right? Can we
Say it
use
again?
Arrowhead plot are used in ferromagnetic materials, right?
Yes.
Can we use it to describe antiferromagnetic or ferrimagnetic transitions, Professor?
Ferrimagnetic, definitely.
Yes.
No, they're not for antiferromagnetic because there's no net moment in antiferromagnet. Yeah, they are used though to analyze antiferromagnetic materials by applying fields and other tricks. It's all part of the toolbox that people have for analysis.
Okay. Participants, please post your questions in the chat box. Professor, we have a question from Professor John Phillip. Can I read it? Among all
wait a second. I have to go to the chat to read it. Yeah.
Yes, Professor.
Okay. From John Phillip says, among all your research contributions, which work gives you the highest happiness today? Well, what a great question. The answer is this one. This is the best thing I've ever done because it's simplicity and it involves information and it probably has applications in every field of thought. I'm not up to being able to do that at my age. The mind doesn't work that well, but you can. But I still have imagination, and my imagination makes me believe that I've opened up a whole new world for people to think about. And you got to say, no one is more surprised than I am that I'm still able to do this at my age. Because I know how many mistakes I make. One of the advantages of working on a computer is to keep track of every mistake you make. And I can prove that my rate of mistakes is increasing with time. But I'm still working. Thanks very much for that question.
Professor, I know you have been you acted in a documentary named Portrait, right? What can you share your experience about that?
Well, I have a brilliant granddaughter who's
nice.
Who is a filmmaker, And the success of that portrait is because she and her partner, Ahmed Ragheb, thought out all those questions. And what makes that documentary work is they are my responses to the questions. And it's the brilliance of the questions and the composing of that that makes that such a successful documentary. It is a work, it really is a portrait. It is a way of showing how somebody thinks and what they think about and so on. I think it's quite remarkable. Despite the fact it's about me, it's really about my wife more than me. Yeah.
There's another question, Professor, in the chat box.
What is your advice for the younger generation working in areas of physics? Have fun. That's you. You can justify it if you enjoy it. It's not a way to. It's not a way to promote yourself or promote anything like that. It's really. What's that? There's a question here. Can you able to explain about Philadelphia experiment producing a magnetic field around a boat to disappear the person in the boat, which is used by the U.S. Navy? I don't know about that at all. I'm completely unfamiliar with that. I don't know.
There is another question, Professor.
Okay.
Let me read it for you. Professor, as you are 93.5 years old, you have witnessed the transition era of technology and science. Do you think you have witnessed the transition of era of technology and science?
I'm sorry, I didn't follow that question.
The question is that you have lived long enough to witness how the science and technology have made transition over the years.
Oh yes, yes.
Yeah. So
do
you think it is going in right direction?
What I predicted in 1985 at an international conference, that the future of physics was going to be women. We had gone from what we call reductionism, where the idea is to get to the root of the problem by throwing everything away and finding out what was important, to where what we're trying to do is do the opposite. We want to start with the roots of the trees and be able to explain out all the leaves. And that is the female of the species has a better mind for that statistically than does the male of the species, who wants to settle on one thing and ignore all the others. And so in 1985, I said that the future of physics was in women in physics. And I'm sure glad you're part of it.
I'm very happy to hear this answer, Professor. There is another question.
Oh yeah, there's still many surprises to come because we have not solved the problems. They're still there. The extremely important problems are still there, but we do make progress, and the progress goes on and on and on. All the stuff they know to do with black holes and so on, it's just fantastic. And the question about dark matters and all the other things that are going on in the universe, we still don't understand the universe we live in, that's for sure. And there's great mysteries. But I gathered from what I heard yesterday was that they've been able to account for 35% of the missing matter by taking something into account. Now, unfortunately, I haven't repeated this to anybody after I actually read it. So I can't remember what it was, how you make the argument, but it has to do with with all the fluctuations which are involved, but I can't remember how they got rid of 35% of the missing. They recovered 35% of the missing matter somehow or other, and that was just in the last couple of days. This is an exciting world, but if you want excitement, though, you go to astrophysics. In astrophysics, there's just so much going on. The best investment ever made by any of the scientific communities was to put up the Hubble telescope. I mean, that's the best spent dollars in the history of the universe. They're looking out and seeing everything that we had no idea about. And so I just love the Hubble telescope.
Okay, that's lovely. There is another question, Professor, from Ardra Ketri. Can I read it? My teacher told me that in every decade, something amazing is happening in magnetism field, and we have heard about some. What are your views, Professor?
Well, I just know that we're in for a great. We have more and more people working, more brains are finding things to do, and they're doing it for the right reasons in many cases. They're doing it because they enjoy doing it. And as I said, I'm delighted to see so many women.
Okay.
Thank you for you traveled. There was a moment when the routine travel was extraordinarily exciting. Were there times when you were bored to travel so long? No, I always had my dog with me. And he and I would carry on conversations as well. Oh, wow. Yeah, that's the kind of thing that I don't know about. And I'm delighted to see that. That's fantastic.
Okay, that update is from Professor Ishwar Reddy. He's working in Indian Institute of Astrophysics, Bangalore.
Yeah.
Yeah.
Yeah. What the talk the other day with
Thank you, Tony. That was wonderful talk.
Thank you. The talk the other day talked about using an accelerator to maintain a subcritical reaction. I thought that was very good, a very interesting idea. And it seems to me that that's a marvelous source of energy. So I think you've done a great job, Swati, in bringing this stuff together, because yeah, I hope that all the ones at your university who are listening to this will go on and do better and better things.
Thank you, Professor. It's a teamwork. The credit goes to our entire team. And I have to thank you for your lecture. It was profound and it was real. You took us through you presented us all your research results and you narrated it like a story. It was like watching an autobiography, and you shared your research experience from start to end, which contained your success, your failure, difficulties you faced, breakthroughs you have made. So it was really motivating, and I'm sure it will help the participants to reach great heights. Thank you, Professor, for your time and effort.
Well, thank you for inviting me. Yeah,
Yes, sir.
This really was an experiment. I had no idea I could do this at my age. And it wasn't clear to me that I could do it until about 4 hours before the lecture. When
you were perfect, Professor.
That's when I put on the slide about the thermos bottle. That thermos bottle was added 4 hours ago.
This dedication indeed makes the fascination of the participants into aspirations. Thank you, Professor.
Yeah. Okay.
Could you please stop the sharing? We can move to the next.
Oh, yeah. Okay. I go up here and say, your screen sharing, share. I did it. Okay. There you are. Now I see you.
Okay, Professor. So let us move on to our next talk.
Okay. Now I'm going to turn off my mic. Yeah.
Yes, sir. Mr. Atul, can you please share the slide? Moving on to our next talk, I am absolutely thrilled to introduce our next speaker, Professor John Phillip, the head of Corrosion Science and Technology Division and Smart Materials Section in Metallurgy and Materials Group, IGCAR Kalpakkam. Also, he is a professor at Homi Bhabha National Institute. He is a prolific researcher in the field of condensed matter physics, and his research interest includes soft matter physics, nanofluids, and their applications. He has been named in the top 2% scientist list in the world, published by Stanford University in 2020. He is an elected fellow of the National Academy of Sciences and an acclaimed scientist with over 290 publications, 6 patents, 13,000 citations, and a H index of 52. He has received the highest prospective research grant of rupees 7.6 crores from Board of Research in Nuclear Sciences, Government of India. And as a principal investigator, he has executed Indo-French, Indo-Russia, and 3 other planned projects. He is the recipient of many prestigious awards, such as Homi Bhabha Science and Technology Award, Science and Technology Excellence Award, Distinguished Faculty Award of Homi Bhabha National Institute, MRSI Medal, INS Gold Medal, Ron Halmshire Award of British Institute of NDT, etc. He served as the editor-in-chief of Journal of Nanofluids of American Scientific Publishers, and he is a member of editorial board in several journals, and he is also council member of several institutions, including Department of Science and Technology, Government of India. His work on ferrofluids has appeared in the movie Black Magic on the UGC channel of Doordarshan and in many media. We are grateful to Professor Phillip for accepting our invitation on such a short notice, and I extend a hearty welcome to the professor to deliver his lecture on interesting optical properties and fascinating applications of magnetic nanofluids. Over to you, Professor.
Thank you, Sadi, for the kind introduction. A very good morning to one and all. First of all, I would like to thank the organizers of the International Symposium on Physics, Fascination, and Aspiration, especially Ms. Swati, Dr. Justin, and other organizers for having me for this lecture today. It's an honor and privilege to deliver this talk. And I listened to some of the lectures yesterday and today. Great talks. The one just before, Professor Tony Arrott, it was wonderful. And I have a difficult task ahead. So let me also take this opportunity to congratulate the Optica team for organizing such an important event by bringing in eminent experts from diverse disciplines, including people like Professor David Wineland and Professor Arrott. Surely these talks should ignite the spark in science in the minds of young students. And I congratulate the Optica team once again for this particular event. Today, I will talk about magnetic nanofluids, some of their interesting optical properties and applications. Swati, can I share the slides now? Yeah, you have
Yes, Professor.
given the privilege. Able to see that now?
Yes, sir, it is visible.
Yes, yes, okay. So basically, I want to share some optical phenomena in magnetic nanofluids that fascinated me and my students over the last 2 decades. So this is how my talk is organized. I will briefly introduce the 2 materials. These are the magnetic nanofluids. The one you see here in this picture. Yeah, the one you see here is a black fluid, and the other in golden color. These are the two fluids I'm going to talk about today. So in the first part, I will briefly introduce these fluids, their properties and preparation aspects. And then I will talk about the optical properties exhibited by these fluids. For example, the scattering from this nanofluids, the transmittance, how it is affected under an external magnetic field, how we can observe Bragg reflections using a white light, using nano emulsions. These are the things. So why I specifically showed this figure here is the scattering from different scatterers of different dimensions gives rise to this kind of effects. For example, the blue color of the sky and the white color of the cloud. These are manifestation of scattering of light by either molecules or scatterers which are larger in dimension as compared to the wavelength of light which is scattered. So these are the this is a wonderful model system to probe different regimes. For example, the Rayleigh regime, where the scattering is due to small objects or scatterers. And using a magnetic field, you can tune the scatterer size in these systems, and you can probe the Rayleigh regime, the Mie scattering regime, and you can even go to the geometrical regime. So it's a wonderful model system, and also these properties makes them ideal candidate for many potential applications. That is what I covered in the second part of my lecture, where I'll be talking about the applications of this magnetic fluids in analyte sensing, for example, the cations, gas sensing, how these fluids are used to detect defects in ferromagnetic material. I will also show you the application of this fluid in optical filters, optical limiters, biomedical applications, and so on. So this is how my talk is organized today. First, let me introduce what are magnetic nanofluids. They are suspensions of nanoscale magnetic materials. I call it magnetic materials. In general, you see magnetic nanoparticles, but you have two-dimensional and three-dimensional nanostructures and materials. If you can disperse them uniformly, like the one which is shown here, that can also be called as a magnetic fluid. The original magnetic fluid was produced by Steve Papel of NASA in the year 1963. It was called ferrofluid because the term nano was not there at that point of time. People used to tell the nanoscale structures as ultra fine or extremely fine materials. But now we call it nanoscale materials with the dimensions ranging from 1 to 100 nanometer is defined as nanoscale material. The beauty of the system is the size of the materials in a magnetic nanofluid is so small that the thermal energy is sufficient enough to maintain Brownian movement of the particle, like what is shown in this animation. So this is not possible if the size of the particles are large. I will talk about the issues with dispersing materials of high density in fluids in the next slide. So when this ferrofluid was prepared in 1963, a guy who was working for NASA, obviously the interest was in liquid fuel, how this material can be used as a liquid fuel, so that with a magnetic field, you can manipulate this fluid in gravity-free environment. This was the idea. Of course, This is not used in liquid rocket fuel, but it has led to many interesting applications. For example, in the hard disk drives that we use today in our computers, use this ferrofluid, a small quantity of ferrofluid, which prevent dust and other particles entering the storage device. It is used in high quality loudspeakers for heat transfer applications. It is used in dampers, in miniature systems where it is used. It is also used as sensors, for example, in inclinometers, accelerometers, flow meters, tilt, vibration, pressure, and level sensors. You can see whole lot of applications for this fluid in all these fields. It is also used in optics. For example, you can create photonic band gap crystals using this kind of materials. Optical switches can be made, and it is made with this magnetic nanofluids. And magnetic nanofluids are widely used in biomedical applications. For example, the drug delivery, cell labeling, MRI contrast, it is used. It's a biocompatible material which is used in MRI contrast. And now people are trying to use this for cancer therapy, and also a host of applications in biosensors are developed using magnetic nanoemulsions and nanofluids. And the term ferrofluid was introduced by Rosenzweig and his colleagues, and he's the one who evolved a new branch of fluid mechanics called ferrohydrodynamics and improved the preparation process and understanding of the magnetic phenomena or process that are happening in ferrofluids. And this fluid also respond to a magnetic field like the one which is shown here. With a magnet, you can manipulate this fluid quite easy, and you don't need a very high magnetic field to do this. And as a result, this is also in recent years called stimulus responsive or smart materials. In general, stimulus responsive materials are materials that can respond to a stimulus. And in this case, stimulus is a magnetic field. When you subject this fluid to a magnetic field, you can see the properties are changing. I'll talk about this a little later. Now, Professor Tony has talked about ferromagnetism, the bulk materials. Beautiful. He has discussed various interaction and various effects that you can see in ferromagnetic materials. But here what you see is the particle size is so small. The suspended particles are either ferro or ferrimagnetic materials, which are disposed in a fluid, as I told you before. So the magnetic properties of nanoparticles are distinctly different from the bulk magnetic property, like any other nanomaterial. That is essentially because of the surface atomic contributions with the surface atoms with the broken translational symmetry and a whole lot of other effects, including quantum confinement and so on. So if you take a ferromagnetic material, bulk material, you can see multi-domains. So on reducing the dimension of ferromagnetic materials, you see the coercive field increases. And in this case, what happens is the multi-domain state at larger size is energetically favorable when the energy required for the formation of domain wall is lower than the difference between the magnetostatic energies and of single and multi-domain states. As the particle size is reduced, the movement of domain walls is restricted, leading to an increase in the coercivity in the multi-domain state. That's what you see in this particular figure. And beyond a size called the single domain size. So below this dimension, you can see single domain. Multi-domains are not seen. And then the coercivity decreases and it drops to 0 at a length scale, which is called the critical size for superparamagnetism. So you have single domain and multi-domain structures. And in the single domain, you have a superparamagnetic limit below certain size range, which depends on the magnetocrystalline anisotropy, whereas the single domain size depends on the magnetocrystalline anisotropy and saturation magnetization. So in the case of iron oxide, which is widely used in ferrofluids, the DS, that is the single domain size, is around 125. You can see different values reported by researchers. So that's why I have been indicated around 128 nanometers. And the single domain size for superparamagnetic nanoparticle is around 20 nanometers for iron oxide. These values are different in different systems. So in layman's language, if we take ferromagnetic material, you see this kind of, coercivity and permanence. Whereas in the case of paramagnetic materials, you see this is the curve, which is shown here. And this is the typical magnetization curve of a superparamagnetic material. So the magnetic moment as well as the susceptibility value is extremely high in the case of superparamagnetic, and they can be saturated at very low magnetic field as compared to superparamagnetic. So superparamagnetic materials can be magnetized and saturated at a much faster rate as compared to paramagnetic material. This is because the superparamagnetic nanoparticle has a macro spin with a very large magnetic moment and susceptibility, essentially because the magnetic moment is sum of the magnetic moments of all atoms in a crystal, which are typically about 10⁻³ to 10⁵ times more as compared to other paramagnetic materials. And you also have to know that all the properties, the magnetic properties, are size dependent, especially when the size is below 20 nanometers. You can see dramatic change in the behavior or the properties, magnetic properties like magnetocrystalline anisotropy or blocking temperature, the saturation magnetization, all these values changes. And what is shown here is the magnetic nanoparticle size, the saturation magnetization, and the magnetocrystalline anisotropy value obtained from the blocking temperature in iron oxide nanoparticle. So now you may have a question. You know that a magnetic nanofluid or ferrofluid has suspensions of magnetic nanoparticles. So the question is, can we simply suspend particles in a base fluid like water or an oil? The answer is yes, if you know the tricks and chemistry. After all, in 1857, Michael Faraday demonstrated how to make colloidal gold, and it is still there in a museum in London. Okay, so if you know the chemistry, you can prepare stable nanofluid. Stable means the fluid where the particles are uniformly suspended, like the one shown in the left image. This is what it happens over a period of time. You can see phase separation, or particles are aggregating and it is forming agglomerates, and they are settled at the bottom of the container. And if you wait sufficiently long enough, you would see a complete phase separation if you try to dispose nanoparticles, even though they are extremely fine. So this can be understood by looking at the sedimentation of particles, which depends on the drag force and the gravitational pull. So the settling or sedimentation velocity for a spherical particle at infinite dilution can be obtained by using these two terms, the drag force and the force due to gravity. So you would find that the sedimentation velocity, that is the settling time, depends on the density mismatch. This is the culprit, because you are trying to disperse high density materials in a low density base fluid. But if you use a very highly viscous, obviously, you can slow down the sedimentation velocity. That's what this equation does. But you see here, there is a d square dependent. D is the size of the particles. So there is a prominent role on the size of the particles that are disposed in a fluid like the one which is shown here. So that is the reason why you have to limit the size as much as possible when it comes to magnetic nanofluid or any other fluid. Of course, this is one issue, is the gravitational pull, and you have many other issues too. For example, you know that the nanomaterials are highly reactive. That's essentially because of huge surface area available in the case of nanoparticles as compared to the micron size particle. So you have the von mass interaction. They are under Brownian movement, but you also have intermolecular forces acting between these particles and solvent. So these particles can aggregate when they are at very small interparticle distances. So if you try to concentrate a fluid or nanofluid, you have to add more and more particles to it. When you increase more amount of particles, which is called the volume fraction or the number density of particles in a given volume, you reduce the interparticle distances between the particles in a solvent for a given volume fraction. So this can cause, net attractive interaction between the particles in the solvent that leads to aggregations. When you consider magnetic nanoparticles, though they are super paramagnetic in single domain, there can be interactions because of the applied magnetic field. Because most of the applications, you have to use a magnetic field to manipulate these magnetic fluids. So basically, the surface chemistry and size control are extremely important to produce magnetic fluids with a high stability. So if you have a powerful microscope to see these nanoparticles in these three systems, of course, this is not a magnetic nanofluid, and it is another copper oxide nanoparticles produced in the lab. And this is what the scenario with a microscope, if you see, the particles are well dispersed without any sedimentation. In this case, what happens? The particles are aggregated, and the aggregates are falling down faster because of, the same gravitational force. And this region, you would be able to see some primary particles, and with time, they also aggregate and they settle down at the bottom of the container. So this is what it can happen when it comes to magnetic fluids. To overcome this challenge of aggregation due to the molecular interactions, you can functionalize, or you can use some surface active molecules or polymeric materials, or you can cap it with a non-reactive shell. So the core in this case can be the magnetic material, and the shell can be non-magnetic, but with less reactive, so it will not have. Or you can even functionalize this shell easily with the different functional moieties. That's how you make the fluid stable against the magnetic interactions. So when it comes to magnetic fluids, as I told you, you have three villains which are acting against, these particles remain suspended in the fluid. One is the gravitational field. Second is the field gradient, which you apply when it is used for specific applications or experiment. And then you can have the magnetic agglomerations. By writing down the equations for each things against the thermal energy, you will be able to find out the ideal size to have a stable magnetic fluid. For example, in the case of iron oxide nanoparticles, if you go up to a magnetic field strength of 1000 Gauss, the size limit is around 15 nanometers. So ideally, if you produce particles with a size less than 15 nanometer, it's good to have a stable. So if you have all these things, and if you take care of these three issues and produce magnetic nanoparticles, you can disperse them easily in a fluid. And you see the action of this fluid. So see, this is a fluid with the magnetic nanoparticles inside. It's not highly viscous. And now you put a toy magnet, you can invert the vial. So it's almost like a solid magnet. And when you remove the magnet, keep it away from the vial, you see the fluid is flowing. And there is no magnetic agglomeration, even if you subject this to a strong magnetic field. That's what you're seeing. The moment you remove the magnet, you see the particles are dispersed immediately. So this cannot happen if you have a fluid with a ferromagnetic material, and if you have a fluid which is not properly functionalized and capped. So what happens if the surface chemistry is not taken care? This is what it can happen. Okay, so you have similar 15 nanometer size particles dispersed in a fluid, and what happens if I apply a magnet? The liquid is separated, but the magnetic nanoparticles are attracted by magnet. You can agitate it or sonicate it and redisperse it. But under a strong magnetic field, you have the magnetic agglomeration of this particle. That is the reason why you are seeing the particles aggregate. So the message is simple. You need to produce particles of desired size. You need to take into account the surface chemistry. If you do take care of these two things, you can produce stable magnetic fluids. Now, how do you produce these materials? You can go either for the top-down approach, or you can go ahead with the bottom-up approach. And I have listed some of the techniques which are widely used, and the one in red color are the techniques that we use in our labs. Co-precipitation is the simplest among all these techniques, where you get particles of desired size. Though you don't have a very good control on the surface morphology, you can get particles of desired size by playing with the reaction conditions. So these are the important challenges ahead when you produce this magnetic nanoparticle. It's important to have particles of similar sizes and surface morphology. What happens if they are of different sizes? The magnetic properties are different, so they don't behave in the same way under a fixed magnetic field. And the switching and other applications, this is a major problem if you have particles of different sizes. And in some cases, you need, particles of certain magnetization or magnetic property that is achieved by tuning the size of the particle. And morphology is also important, because some of the properties like magnetocrystal anisotropy or the shape anisotropy, all these parameters changes with the surface morphology. Monodispersity is the most important aspect you need to take into consideration when it comes to practical applications. Minimum polydispersity is ideal, so that all the particles in the fluid behave in a similar fashion when it is subjected to a magnetic field. The purity is important because if you have impurities, it can hamper the magnetic properties in a big way. And the functionalization is important for making nanofluids. As in nanoparticles, you need not functional, but again, you have the aggregation issues if you want to use them as individual particle, and a long-term stability, because these fluids, once you produce, it should remain stable for a very long time. This is another requirement. And high temperature and size dependent properties, and these are some of the materials which are which we have been working for the last 2 decades, and these are the students, chemists, work in this particular topic of synthesis, characterizations, and applications of fluid. For thesis work. So I summarized everything in a few slides. Now, if you take, I just want to show 1 or 2 slides on co-precipitation. This, you use salt of proper stoichiometry, and you can add an alkali to start precipitation, and you can arrest the growth of nanocrystals by adding surfactant or a surface active species, which can be even polymeric material. And then you can get the particles from the solution and, dry it and redisperse in the solvent where you want to disperse them. Obviously, the compatibility of the surface active moieties with the solvent is an essential requirement. So by playing with these parameters, the reaction time, pH, nature of alkali, the digestion time, ionic strength, solubility product of the solvents that we use, etc., you will be able to tune the size of the nanomaterials that are produced. So this is what I have been telling, that once you cap it with the functional moieties, organic layer, or a surface active species on the surface, and if you go to a high resolution TM, you can see the lattice planes and the crystal here surrounded by an amorphous layer here. This is because of the surfactant layer on the surface of these nanoparticles. This is essential. This is typically less than a nanometer, or 1 to 1.5 nanometer is the thickness when if you use a fatty acid surfactant like oleic acid molecules. The second fluid I've shown is, this golden colored fluid, which is again a byproduct of the ferrofluid, which is prepared with, an emulsifier and water to make droplets of larger sizes. Why this is done? Because, the nanoparticles in the case of ferrofluid or magnetic fluids, the size of the particle is so small, and, you cannot see them under an optical microscope. But if you produce an emulsion, you can tune the size so that you can go from 10 nanometers to even a micron sized droplets. And these droplets are again magnetic. With a magnetic field, you can manipulate them. I will show you some movies on this. So here again, if you take the emulsion droplet, inside the droplets, you have the magnetic grains, which are of iron oxide, and there are many applications. And you will be able to get particles or the emulsion droplet with a fairly monodispersed size distribution. That's what is shown here in the DLS curve, which is taken with this kind of emulsions. Now, how this is produced, it is quite easy to produce this fluid, and you can take the ferrofluid and mix it with the surfactant water, and it's a process of fragmenting this oil droplets and dispersing them in the water, which is the continuous phase here. So you have the droplets with the magnetic grains inside, different number of particles initially in the crude emulsion you will see, and then you can do the fractionation. It is a process to get fairly monodispersed emulsions, where you use the attractive entropic force due to the exclusion of misers from the interparticle spacing, which leads to, separation of droplets with the different sizes. If you do this, you will be able to get fairly monodispersed emulsions. Now, you may ask why these emulsions are required. As I told you, the emulsions, you can make droplets with the different sizes, and the sizes which you can also see with a good phase contrast optical microscope. In this case, you can see the effect of a magnetic field on these nano droplets, and this you can see with an optical microscope like the one in my lab. So in this particular case, we also make a magnetic trap here to control the magnetic field. With the controller here, we can change the distance between the jaws and get magnetic field of desired size, the desired magnetic field strength. So in this video, you would see the action which is seen with an optical microscope, which is not possible in the case of a magnetic fluid or ferrofluid alone, because you need a transmission electron microscope. Again, in transmission electron microscope, it is not possible to see in situ the movement of particle or the Brownian motion. Whereas in this case, you can see the droplets with the nanoparticles inside without a magnetic field. You can see they are, they are under Brownian motion at room temperature. But the beauty of this system is that they are magnetically polarizable. That means the grains inside the droplets, the magnetic grains are randomly oriented without the application of magnetic field. But with magnetic field, you can see the grains are orienting along the direction of magnetic field because of the magnetic dipolar interaction. And then you can create one-dimensional, two-dimensional, or three-dimensional structures in the fluid, depending upon the number density of droplets and magnetization properties of this droplet. And here you see a movie. So this is with a strong magnetic field. You can see the nano droplets, which are typically around more than 200 nanometer. That's why you are able to see with an optical microscope. And they are forming one-dimensional array. That is what it is shown. It is a movie. I will play it now. You can see this is with a strong magnetic field. And now I remove the magnetic field. You can see the droplets are under Brownian motion. There is no order in the system. So you can create ordering, and you can, assemble these nano droplets the way you want. And, you can use this as a model system, drop molecular interactions. And okay, this is fascination. And this is the fascination, we got when we observed this first under microscope almost 15 to 20 years ago. Now, then we try to understand why this kind of ordering is taking place in the case of magnetic fluids. So we understood that, these emulsions are stabilized with the surface active species. As a result, you have electrostatic repulsion between the droplets. So the droplet surface, you have charges if it is stabilized with the surfactant, or you can even stabilize with polymeric material where you have steric interaction, or if you use a polyelectrolyte, you will have electrostatic plus steric interaction. But the force that bring these droplets together is the magnetic attraction, which you can calculate for an infinitely long chain here. It depends on the magnetization and this distance between the particle. And of course, the van der Waals interaction is effective at very small interparticle spacing, but the magnetic interaction is relatively long range as compared to the van-der-Waals interaction. That is why we are able to bring these droplets together. And, by doing this, you can also get information about the molecular interaction. And we have done a lot of work, but I will not be discussing about them due to positive time. And also it is not an area listed in my outline. So these are the initial papers that we published on this work on the molecular interaction. The beauty of the system is, you don't need X-rays to see the ordering in the system. This is the beauty, the real optical effect that we can manifest with a pocket-sized spectrophotometer. So you can see the photometer here. And, with a magnetic field, you can see the Bragg peak appearing. The Bragg peak is seen because of the selective reflection of light in this direction, if it is eliminated from the backside of the emulsion. So if we make a solenoid like the want, where we can also thermostat it, we can control the temperature, and you shine it with the light and collect the reflected light, it goes to a spectrograph, and magnetic field of this coil you can precisely control using a programmable current source. And then you will be able to see the Bragg peak changing with the magnetic field strength. So this is the real manifestation of the Bragg peak in a ferrofluid emulsion. I'll play it. This is with a strong field. This is a particular D-spacing, and the D-spacing is increasing when you reduce the magnetic field strength. So in this case, I have applied a strong magnetic field to bring all these droplets along the direction. These are one-dimensional changes because the volume fraction is low. And what is happening here is, by removing or decreasing the magnetic field, you can see the Bragg peak is shifting towards this direction. That means the D-spacing is increasing, the wavelength is higher, and at some point, when you drop the magnetic field, or the magnetic field is so small, the dipolar interaction cannot happen at all because the thermal energy is overtaking the magnetic interaction, and the Bragg peak is disappeared. You see the beauty of this system? You produce crystals, you can see the ordering that are happening in the system. This is the most recent work, and if somebody is interested, they can read this paper, how to create different kinds of structures by using this magnetic nano droplets of different properties. And you can see hexagonal, lamellar structure, Benwall structure, Lebridge structure, with a magnetic field strength varying from 30 Gauss to around 150. It's very, very meager magnetic field. That is what you need to create this kind of ordering. Now imagine you put it in a big, in the cell and concentrate, or you go for higher volume fraction, you can create crystals also using the same technique, which is being done by some groups. So what are the interesting and unusual properties of magnetic fluids? One, I will show in this video, the location of the fluid can be remotely controlled. So what I have done to demonstrate this to you, I keep this fluid in a vial between the pole piece of an electromagnet. This is the electromagnet, and initially I apply a strong magnetic field. I create a strong magnetic field. The fluid is drawn towards the pole piece area. Now let's see the movie here. So this is with the magnetic field on. Now slowly I decrease the magnetic field. What happens? The fluid is drifted away from the magnetic field. That means the gravity has pulled it down. So this fluid can defy gravity with the help of a magnetic field. You see how it is drawn towards the magnetic field. So this is the pole piece area where the magnetic field is maximum. It remains there. As long as there is magnetic field, the fluid remains in that space. This is what it is used in dynamic sealant and static sealing applications. So, you know, chameleon and butterflies, all these things, you can see structural colors. These are not real pigmented colors. These are colors generated by structures, the nanostructure. And similar color changes can be manifested in a ferrofluid emulsion. That is what it is shown here. With a magnetic field on, you can see the color of the fluid is changing. And, you know, you end up with all kinds of colors by varying the magnetic field. You can get the desired color. That means you are creating gratings of different in the droplets. Yesterday, Dr. Murugesan was, my good friend, Murugesan was talking about lithography and creating Bragg grating and other structures. These things can be created in a fluid. That's what it is demonstrated in this particular video. So I'm sure this is quite fascinating to many students who have seen this for the first time. It's a unique material with liquid and magnetic properties. You have seen that how the liquid is drawn towards the magnetic field and how they are manipulated. And the location of the fluid can be remotely controlled. And it has an ability to conform to any geometry. And it exhibits very interesting optical, thermal, and microstructures, rheological properties, and so on. I don't have time to discuss all this work we have done, thermal properties, a lot of work is done. And this system, the dimensions are comparable to bioentities, and it has a lot of interesting application. I think I have only a few more minutes, right, Saudi?
Yes, sir, but you can take your time.
No, but next speaker
Yes,
is
next speaker is next session starts by 11:15.
okay, so I have another 5. I have to go super fast. Okay, right. So I will briefly tell you about a few studies which are related to the optics or optical phenomena. As I told you before, the order disorder transition can be probed. See, initially, if you take the ferrofluid, the particle size is around 10 nanometer. So the particles are under Brownian motion. That is what you see, where the thermal energy, thermal energy is sufficient enough to take care of the magnetic interaction force. And then by increasing the magnetic field strength, you would be able to create this kind of structures in the system. And then you can have columnar structure. And finally, you get labyrinth or hexagonal and different kinds of ordering. So in this case, the beauty is you start with the Rayleigh regime. You can go to my regime where the dimensions are comparable to the wavelength of light, which is used here, 632 nanometer. And then you can go to very large structures in the fluid, as shown in the earlier image. So this is the experimental setup we have in our lab to look at the field-induced structural transitions, and we look at the scattered light intensity as a function of magnetic field strength. From this, we will be able to get information about, critical transitions where this kind of structures are formed, then separating transitions are occurring. This is because of the competition between the dipolar interaction energy between the two droplets and the thermal energy. And we've done a lot of work on this, and we have demonstrated that, the critical magnetic field for different kinds of phase transition can be identified by looking at a simple experiment just by measuring the transmitted light intensity as a function of magnetic field. So the physics is again quite interesting. These are super paramagnetic without a magnet, the magnetization value, and you induce magnetic moment, which is proportional to the susceptibility and the applied magnetic field. And the magnetic interaction can be attractive or repulsive depending upon the angle between the dipole and the magnetic field strength. And this is the most important parameter, the coupling constant, which decides whether it is to form an ordered structure or it should remain as random structures. Another beautiful work which we have done is that we have demonstrated striking similarity in the scattered light pattern between the nanostructures and macroscopic objects. This is an experiment Junaid has demonstrated. He has used an optical fiber of 120 microscope, 120 micron, and then he has created 8 nanometer sized nanoparticle array and demonstrated that the scattered patterns from the nanostructure resembles that of the patterns which are formed with the microstructures. And by analyzing the diffraction pattern, you can even get the information about the diameter of the structures. So the onset of one-dimensional or two-dimensional nanostructure formation, the orientation, the diameter of nanostructures, etc., can be probed using scattering and diffraction studies. This is the message I want to give. And you look at how this how the light is scattered. This is the transmitted light spot from a ferrofluid sample. And at some point, the transmitted intensity is so intense and you don't see any light coming out. There are a lot of interesting physics in that. And then because of the nanostructures, I don't know whether you are able to see, you can see the ring-like structures which are formed. And this is because the structures, the nanostructures are aligned along the direction of the magnetic field and and the light which is scattered at a very small angle of incidence, which gives rise to this kind of structures in the fluid. So we have also done a lot of work on analyte sensing. Again, the color changing phenomena, which is used to detect analytes in from solutions. So we functionalize the droplets and then look at the Bragg peak changes or the interdroplet changes that are happening in the system. By doing this, you would be able to get the information about the concentration of ions. This is the quantitative measurement, but the qualitative measurement, you would be able to tell that, your water is potable or the ion concentration is beyond the tolerance limit. That can be detected by looking at the color change in the emulsion itself. So we have also done this with respect to glucose, and we have done a lot of studies and measured the concentration range of glucose that can be detected by looking at the Bragg peak change, either the blue or red shift in the system. And this can also be used as a temperature sensor. You can use a thermosensitive polymer, and again, this polymer behaves differently with the temperature and change the despacing between the droplets which are in the solution. That's the working principle used in temperature and pH sensing. The last application I want to show you is detecting defects in material. Obviously, this is a requirement when it comes to rail track, oil and gas pipeline. These are all the components are made of ferromagnetic materials, and a technique is available for that. It is the Hall probe array, which is used to detect the leak magnetic flux. So if there is no defect, you will not see any leakage magnetic flux. If there is a defect, you can see the there is a leakage magnetic flux. That is what it is. So when I observed that, we can see color changes with the small magnetic field, this idea came to my mind. And then we have demonstrated that the defects in ferromagnetic materials can be manifested using this emulsion. Here there is an animation. This is without defect and magnetization. And when you magnetize, you will be able to see the place where the defect is buried, and the rectangular and cylindrical defects in the material. So the color changing property of the fluid can be used again, selecting one particular wavelength from a white light. This is another applications we have demonstrated and a patent on this. And the last one is the biomedical applications where, the relaxation time, Neil and Brownian relaxation of these nanoparticles are used to, obtain the temperature of desired temperature in few minutes to half an hour by using this magnetic property. I don't have time to discuss that, but a lot of work is done on this. So I conclude this by saying that the magnetic nanofluids are a class of smart or stimuli responsive material that can be manipulated with a magnetic field. They exhibit very interesting optical properties that have been exploited for applications in defect detection, analyte sensing, cations, anions, gases, and so on. And it can be used optical limiters, optical filters, and it can also be used as a model system to probe ordered disordered transitions, scattering, and diffraction phenomena. You get a lot of new insights, and even you can quantify the kind of structures that are formed in the fluid by just looking at the scattered. So this I showed two materials. Materials are the ingredients for any technology. Say combining, these are the building blocks. The materials are the building blocks for technology. So combining imagination and creativity, you will be able to make meaningful devices. That's what I've shown. For that, obviously, imagination is more important than knowledge. That's what Albert Einstein says. And, imagination has no boundaries, whereas knowledge has a boundary. So I conclude my talk by telling a story from Rabindranath Tagore. It's a story of the sun and a candle. When the sun went down in the evening, he asked everyone on earth who will take up my responsibility of providing light. No one replied. A candle in a log cabin answered, "My Lord, I cannot light up the whole universe as you do, but I will do my best to light up the small room." So I've done the job of a candle. We have heard lectures from eminent experts and Nobel laureates and so on. David Wineland and Tony Arot. These are the people, and I try to do the job of a candle with my limited knowledge in the field of magnetic nanofluid. Thank you very much, and I thank all my students who have contributed to the slides which I've presented today. Thank you. Thank you for your attention.
Thank you, Professor Philip. You indeed enlightened the participants with your valuable presentation. Can we quickly take the questions, sir?
Yes.
Yeah, so I ask participants to raise your hands and also post your questions in the chat box. There are already some questions in the chat box, so let me read it for you.
Yeah.
We know instability is one of the major problems with magnetic nanofluid. So according to you, what are the main causes of the instability and how we can remove these? Is there variation in stability with variation of synthesis process? So this question is from Anurag Kumar Singh.
Yeah, very good question. So actually, your question has two parts. The first, instability, probably you are referring to is the kind of spike that you see with a magnetic field. So this is something which is very well known to the physics community. The magnetic force and the surface tension, these are the two things. So the with magnetic field, you would be able to see the spiky structure in a ferrofluid. That's the instability you're talking about first. And this instability is, you can overcome by applying strong magnetic field. That is what it is used in many practical applications. The second instability you refer is the stability issues because of the aggregation process that are happening in the magnetic fluids. So this is a real problem to produce particles or fluids with the long-term stability, which is absolutely essential for all practical applications. Okay, so this can be taken care by tailoring the particles of desired sizes and the surface chemistry, as I elaborated in the first part of my lecture. So these are the two things you need to take care of, because otherwise, you have this the magnetic interaction and also the dipolar, or that is the dipolar plus the van der Waals interaction. These interaction can give rise to instability in the system. And if you have systems with a broad size distribution, this is one thing which is which is giving problem to most of the fluids that are synthesized in the laboratory. That's the reason. The reason is very simple. You see, you have a mixture of ferromagnetic and superferromagnetic particle. So the ferromagnetic particle with a size greater than 128 or single domain maybe, but it's not super permanent, 20 nanometers if you take, they can form aggregates and the fluid can become stable. So that's the answer to your question. Yeah.
Thank you, sir. There's another question from Ms. Shiba Anandi. What is the threshold concentration for the particles in the suspension to act as nanofluid? Which parameter of the magnetic nanoparticles and the suspended medium majorly differentiates nanofluid from mere dispersions?
Let me read the question. You are referring to
Shiba Anandi.
right?
Shiba Anandi.
Anand. Okay. What is the threshold concentrated particles suspension to act as the nanofluid? There is no threshold concentration. It depends upon your applications. For example, if you want to use it in the sealant, you may need a high concentrations, and that is essentially because you want to retain the fluid at the place where you want this to remain. For example, in the pole piece of a shaft or other geometry, there the concentration can be something like 15 to 20% will be the suspension volume fraction or the weight percentage. Whereas if you take heat transfer application, you don't need much high concentration, so you can use something like 5 weight percentage. And if you want to use it for the kind of studies which we have done, the optical properties, you have to limit the concentration even below a few percentage. It can be less than 1% also. So it depends on the kind of applications where you use a biomedical application. You need a very small quantity. The loading can be very, very. So the number density can go between 10 raised to 15 to 10 raised to 18, depending upon the application in terms of the number. Which parameter the magnetic particles and the suspended medium majorly differentiates nanofluid from their dispersion? See, it is again, if you want to use it for biomedical application, you need a aqueous magnetic fluids. In the case of sealant, you don't go for aqueous nanofluid. You want to dispose in a low, vapor pressure organic solvent. So that is what it differentiates different dispersants. And now I can go to the next question quickly.
Sir, before that,
Priya.
Mr. Shukdev Pandey has raised his hand. You can ask your question, Mr. Shukdev.
Good morning, sir. Am I audible?
Yes.
So yeah, thank you for this wonderful lecture. So it was very informative. I think I missed something in between. So my questions were, I had two questions. I think you answered one of them. That was about the density of the ferrofluid that is required, and the other question I had was about the thermal effect. Like, what are the general temperature ranges, like, if we talk of applications? So, and with these different applications, do we kind of have to choose different materials, like the nano magnetic materials, according to the application?
Yeah, very good. Okay. So this is again, if you take iron oxide nanoparticle, the Curie temperature is quite high. Okay, so it can work up to 555, above 500 degrees centigrade. There's no problem. But the problem is only with the carrier fluid or the solvent which is used. So if you use water-based system, it cannot go beyond 70, 80 degree. But you can go for oil-based system where you can go up to 200, 250, and some of the solvent you can go even beyond that. So in general, when it comes to fluids, 100 to 200 degrees centigrade, various oils can be used as a solvent for heat transfer applications and all. But if you want, and nothing will happen to the magnetic nanoparticle, even if you go to higher temperature. So the solvent is evaporated from the solution. That's the only problem. So you can go for low vapor pressure solvents, which may be able to work even at a higher temperature, up to 400 degrees. Yeah.
Thank you, sir. Thank you.
Yeah.
Next question is from Ms. Kalaipriya.
Yeah.
How to change the color of nanoparticle fluid by tuning its size in non-magnetic materials?
Very good question. Okay, this is what it is done in different non-magnetic system, the gold, silver, and all. You can see particles with different sizes will be able to give. That process is totally different from what is done in this case. Okay. So there, the size of the particle can be tuned so that you get this surface plasmon resonance, which changes with the size of the material in the case of non-magnetic system. Yes, but in this, the magnetic system, what we are doing is we are changing the periodicity. We have similar particles, but we can tune and different color. That is what you see in the video, which I have shown you, right?
Yes, sir.
Yeah.
Professor Arot has asked a question.
Yes.
What are the costs for commercially available nanofluids?
Cost, yeah,
Yes.
it is quite expensive when it comes to biomedical application, because you need biocompatible materials, and it can cost I think quite high. I don't know the exact price, but it's quite expensive. If you want to buy a few ml, it can cost you hundreds of dollars. With the fluids with very good monodispersity and stabilization. It is available with few companies like Ferrotech is a US company mastered in this technology right from 60s or 70s. They sell this fluid for various applications, biomedical applications. It is fairly expensive, and even sealant. If you take if I remember sealant, ferrofluid sealant, if you want to get something like 10 ml, it can be around $200 or $300. That's the cost of magnetic fluid. But the size of the particles, functionalization, all these things are perfect in the systems that are available with these companies. Yeah.
Sir, let us take one last question.
Yeah.
What is the reason for formation of circular diffraction pattern with ferrofluids?
Yeah, this is, I didn't have time to explain everything, because you have, if you take, see, I want the students to perform this experiment, take a small needle and optical fiber and use a, LED, or you can use a helium laser, and you shine it at close to zero angle of incidence. You get the scattered patterns. The conic section on a screen placed perpendicular to this. But if you analyze the spot area, you would be able to see the diffraction pattern, which again depends on the scatterer size. So I think you can, visit my Google site or ResearchGate sites, and we have done a lot of work. And I will not be able to explain everything in a few minutes, because next speaker will be waiting, and everything is discussed in this work paper. The answer is scattering from the nanostructures that are formed in this system. Yeah.
Thank you, Professor. Thank you for your fascinating presentation. The demonstrations, the video and animations which you included in your slide, it made the concepts very comprehensible, and it also boosted the concentration of the participants. Your presentation was very nice, and your work was indeed very interesting. Thank you very much for your time and accepting our invitation. Thank you, Professor.
It's my pleasure.
Now, I request all the participants to turn on your video camera for a minute. Can we all take a group photo?
Yeah.
And all the speakers, professors, Please turn on your camera for a minute.
I'm not able to see the
Sir, could you
One
please
second.
unshare?
One
Yeah.
second.
Yes.
Yeah, I don't know. I'm not able to see the. I have to unshare, no?
Yes, sir. Yes,
How
it
do I?
is.
Yeah.
You have done it?
Yes,
Okay, great to see Professor Tony. Yeah, right. So
Okay. So let's
Hey,
take some
thanks for a good,
snapshots.
thanks for a great talk.
thank you. Thank you so much.
Thank you, everyone. Now let's move on to our next talk. I request the organizer to share the slide. Professor Reddy, could you please give me a minute? I'd like to introduce you. It's my pleasure. to
Sure,
introduce
sure.
you to this.
No problem. Yes.
Okay.
Should I take it out my thing or stop sharing?
Please, Professor, I'd like to share my slide for a minute. Let us now spice up the symposium with an exciting presentation from Professor Ishwar Bacham Reddy, a leading scientist and a professor in the Indian Institute of Astrophysics, Bangalore. His area of specialization is applying high-resolution spectroscopy to understand stellar nucleosynthesis and galactic evolution. He was a postdoctoral fellow at Valparaiso University, Indiana, and research fellow at University of Texas, Austin. He and his collaborators have recently made a breakthrough in stellar spectroscopy where they discovered the source of lithium's increase in the universe after the Big Bang. Not to mention that origin of lithium remained as a riddle wrapped in mystery inside an enigma for decades, and Professor Reddy, through his diligent work, has solved it successfully. He has been the program director of 30-meter telescope since 2014. This is the world's most advanced and capable ground-based optical, near-infrared and mid-infrared observatory. This is a multinational venture that involves India, United States, Canada, Japan, and China. Professor Reddy is also a designated gardener in the board of governors in this project. We are honored to have him with us in FIFA 21, and I solemnly welcome Professor Reddy to illuminate the participants with his presentation on next generation optical and infrared telescope projects, new windows to the universe. Thank you, Professor. Over to you.
Thank you, Swati, for your kind introduction, and thank you for the organizers for inviting me for this wonderful conference. And then I think you had an array of people talking to you, and then so that's wonderful. So let me go to quickly my presentation mode. Yeah, so yeah, I won't be talking too much about what I'm doing now, since astronomy is a small subsection within the physics community. So I would like to share with you the kind of facilities we have in the country, and then the kind of facilities we are going to have in the country soon, And of course, India's the major international participation, particularly the TMT project, and what we are doing to the project within the country, kind of, developing systems, engineering systems, things like that. And of course, I will touch upon very briefly about my recent current interest in stellar spectroscopy results. So this is the front thing is one of the astronomy, the Granger, it's a UNESCO site. It is placed in Jaipur. It is Jantar Mantar. I think many of you might have gone there and then saw. So it is basically measuring, the positions of sun, and this is the largest sundial in the world, kind of things to measure the time. It's 2 seconds accuracies. And then the various things are there to measure altitude, longitude, and things like that. I think you should visit that place and then see how much the Indians who are interested in astronomy and then measuring these things. So of course, who cares astronomy? Of course, astronomy is one of the ancient fields associated closely with humankind. Of course, farmers required for agricultural activities those days were in the pre-modern era, and sailors for navigation in high seas, they do require various stellar positions to reach their shores. Of course, for culture, calendars and timekeepings are very important to have our own festivals. And as human needs grow complex, so their dependency in astronomy and that phenomena. Of course, GPS works on positions of celestial objects like, quasi-stellar objects, which are the brightest one, which are the far away. So you require some accurate, time positions to navigate through whatever we do complex things on Earth. Of course, like, power, now you are creating now, what happens in the center of the sun, people wanted to create here on Earth. And then, of course, understanding origin of elements on Earth, and then see where they come from and things like that. So, okay. So, of course, we are also now curious about things as we learn more about our physical universe. Who and what are we? Are there anyone else in the universe other than us? How long the sun shines? How this universe came into existence? And how is it going to evolve? So these are some of these very fundamental questions people are going to answer through modern tools, which involves a lot of technology and financial resources. Let me now jump into astronomy facilities in India very quickly. Maybe I will take just 10 minutes to touch upon where we are, so that many of you understand what kind of facilities we have in the country. For example, this is the map of astronomy in the country. You can look at solar observatories are marked here. There's a Udaipur, and then there's Kodaikanal, which you might have gone many times, where Ebenezer is in charge of it. There, of course, there are optical and infrared observatories, which are in the top Western Himalayas. These are one of the best sites in the world for astronomy. And of course, Devasthal, this is in the north, Uttarakhand. And then you have Mount Abu and then Venubaba Observatory, which is again in Tamil Nadu. So these are the major facilities we have in the country. And most of these, like Venubaba Observatory and IAO in the north only, the Western Himalayas, are run by Indian Institute of Astrophysics, Bangalore, which is here. You can see that. Major astronomy institutes, you can see these one physical research laboratories they have, Tata Institute of Fundamental Research, and then Inter-University Center for Astronomy and Astrophysics, Pune. Of course, IIA Bangalore. So of course, we also have the space astronomy. So then now recently we have in the space a full-fledged observatory, which is Astro satellite, which has been there now more than 5 years, and which scans the sky in gamma rays and X-rays and UV light, and then of course also in the optical. Then soon there is going to be Aditya, the mission dedicated to the sun. So this is the Indian Institute of Astrophysics, and which was traces its origin to 1776. So it's more than 200 years of heritage of doing astronomy in the country. And then now the Indian Institute of Astrophysics is established in 1971. Before that, it was in Kodaikanal. And IAA operates one of the largest telescopes in the country, that is 2.3 meter. When it was built, it was the largest in Asia, and which is a full-fledged observatory, which has a number of other telescopes for nighttime astronomy, like a 1 meter telescopes and things like that. So this is around 160 kilometers from Indian Institute of Astrophysics, Bangalore. So you see that beautiful place. This is called Javadi Hills. Might have known. And this is a 2.3 meter telescope dome. It is an equatorial telescope. So yeah, it is equipped with a number of instruments, both spectroscopy and imagers. And then spectroscopy goes, the 500 all the way to 500 nanometers, that 5,000 angstroms to quite a bit, So it has very good resolutions in covering spectral lines. That will come to later what this resolution about. Okay, the entire optical wavelength it covers. This is mostly spectra used to understand nucleosynthesis aspects, stars compositions, and understanding various phenomena in the stars. So these are some of the instruments which are spectrographs we have. And since seeing is not very good, these telescopes now currently used only for spectroscopy purposes, because imaging requires very, very good seeing in the sense atmospheric turbulence. Okay, so the turbulence is measured. The lower the turbulence, better the seeing. Okay, and better the facility for astronomy doing. Astronomers are not very romantic. They don't want twinkling stars. They wanted stars, to see stable stars, without any twinkling. The twinkling is caused by the atmosphere and its turbulence. So IAA also operates very high altitude astronomical observatories, which is in the Western Himalayas, called a place called Ladakh, and which is borders to close to Chinese border, and then closer to Pangangzhou Lake. So again, we have a modest telescope. These are 2 meter class telescope, but then we are preparing for these as a major astronomical facilities in the country by putting large telescopes like 10 meter class telescopes, things like that, which are the proposed telescopes. Why do you want to go all these remote places? Astronomy requires very remote, high altitude places, because high altitude places have the less water vapor. Less water vapor means better transparency, because the water vapor absorbs a lot of infrared wavelengths, so it blankets it, so you can't see it. So we go to higher altitudes, but very remote places, we don't want to see light pollution, and also we wanted to have a very dry places where monsoons are less. These are the places where the monsoons are very little. Okay, no monsoons, actually no rains on this, very little precipitation these areas. So these are best suited for astronomy, some of the astronomy. There are some places on Earth, something like this, So I will talk about as we move forward. So this is the observatory, which is around 14,000 feet above the sea level, and where the oxygen levels are very low. And again, we have, these are the facilities, the modern facilities, the IAA runs there in Western Himalayas. All these telescopes and instruments are controlled from Bangalore through dedicated satellite link. Okay. And here also we have very high resolution spectrographs, giving a terrific, here now we are able to go much the lower wavelengths, high energetic, because that is not possible in Kavalur, because Earth's atmosphere is so much which absorbs the low UV light much more compared to high altitude observatories where the atmosphere is less. And of course, we have dedicated observatories for the sun. IAEA runs in Indian Institute of Astrophysics. You can see this is the place. It is almost like unique in the world, and then we have this data for the sun, almost everyday data for almost 100 years, and now which is digitized. And then there's a lot of interest by solar astronomers, and then solar weather people, which is very important because to protect our own satellites and things like that. So, which is very important to understand the sun and its behavior in a predictable manner. Sun emits a lot of solar flares, and then sometimes which damages satellites. So, so there is a dedicated observatory in Kodaikanal, which is functional close to 200 years. And then we have 100 and plus years data of the sun, and then which is digitized and is available to people all over the world. Again, we have high energy gamma ray observatories, which are again in the Western Himalayas. So there are quite a number of things we are having. These are the facilities. And the Physical Research Lab, PRL, also runs both solar and optical telescopes in Mount Abu, which is, I think, in Madhya Pradesh. And then you can see this. Again, these are all modest 2 to 3.6 meter telescopes, that class. And this is again Aryabhatta Research Institute for Observational Astronomy, which is in Uttarakhand. And you can see these how beautiful these mountains are. And one of them is now, this is now the nation's largest telescope with a 3.6 meter monolithic primary mirror. Okay, this is the largest in the country now. Currently, the 4 meter class telescope, and which is now commissioned in 2015, and then which is now open for observations. Of course, it doesn't have very high resolution spectrographs yet, and then people have to equip that. Okay, that's the telescope we have there. This is again Altazimuth telescope. Yep. That's very quick. Of course, we have the radio telescope. This is the world's the best telescope in the meter wave to understand the universe in radio waves. Many things cannot be done only in single wavelength because the various celestial phenomena is seen in the different electromagnetic spectra. Some are only visible in radio, some are in optical, some are in gamma ray, very high energetic things in the gamma rays and the X-rays and things like that. And the very far away light, and then very feeble, that is picked by the radio wavelengths. So GMRT is one of the world's heavily used telescope across the world. And then 50% of the proposals are from abroad, and a lot of people come and then stay and then do work there. It's one of the largest telescope with 30 discs with 45 meter diameter each one of them, and then provides a greater baseline. Of course, Inter-University Center for Astronomy and Astrophysics provides a lot of facilities to do astronomy, both in theoretical and some in observations. This is a kind of a nodal agency for a number of universities and then institutes in the country, and a lot of people become, associates in that university, in that institute. This is the government of India set up to spread astronomy across the universities, which is now not much across the institutes and then the institutes, but now currently it is now getting much traction among ISERs and then IITs because all these institutes have taken initiatives to produce a number of PhDs. And of course, we have now, this is an AstroSat for different wavelengths, both in X-ray and ultraviolet, and So of course we have the optical, and this is a full-fledged astronomy satellites which is in the space. This is there for more than 5 years, and then this is built by the mostly Indian institutes with Canadians, and now this is open for a proposal for anyone in the country abroad too, and a lot of science is coming from these places. And these are some of the pictures about UV telescope, which was built at IIA here. And then this is which around 40 centimeter diameter. So, and we can see here, this is now currently the only one ultraviolet telescope in the space. And then it is much more advanced compared to the NASA's GALAX ultraviolet mission. The GALAX, you can see one of the pictures of spiral galaxy, and you can see that it's not that well resolved. When you come to here, the images you can see much more sharper, and they're very clear. So these are the things which are quite useful to understand, star forming regions there, because those emit in high energy photons. So those are captured in the ultraviolet. Okay, so this works in near ultraviolet. These angstroms, 1800 to 3000 angstroms, and visible also some of them. So 3500 to 5000. So those are the current what we have both in the space and other places. The future facilities include Aditya, this is dedicated to the sun. This is one of the most advanced telescope, though it's a smaller 20 centimeter, but it is going to be in the Lagrangian point where, the gravitational forces of the Earth and the sun are almost equal. So you all the time you see that, like, if you put that telescope in that Lagrangian circle, and then it all the time moves synced with the sun. So all the time you see only the sun all the 24 hours. Okay, let me see, my charge is getting down. I need to. Okay, so that is going to be launched. It's got postponed because of the COVID, and probably in the early next year it will go up. So this is going to study the solar corona, flares, all kinds of things, how the energy is transported from the center to the photosphere, from the photosphere to corona, because these are, some of them are completely unresolved. There is a corona which is far away from the sun, which has 1,000,000 degrees. On the other hand, the surface of the sun is just 5,600 Kelvin. So this is at the cost of $200 million they are spending. So then this is the Aditya payload, which we just talked about. The number of payloads are there. And then again, India wanted to have one of the largest solar telescope. Solar telescopes, the largest in the world is now 4-meter class telescope. This was recently set up in Hawaii, Mauna Kea, by United States. India wanted to have a 2-meter class telescope. So the current one is around 40 centimeters. So this is going to be in Pangangsu Lake in the Western Himalayas. So that's the background. We can see the Pangang Lake, and the telescope is going to be built here. This is a renderation of that. And then those are the mountains, which is behind that is Tibet. So this is in the advanced stage of approval by the government of India. And of course, we are also now have a proposal for, this is a long-standing desire of the astronomical community in the country to have at least a 10-meter class telescopes in the country. So this is the government is under consideration for approval. So currently now we have a dozen of them run by various countries like Japan and Europe and the Americans, close to 10 telescopes of this nature. But then India does require to have one more here in the country to cater to the needs of our own astronomers. And Hanley is one of the best sites, so which we talked about already. What we require is number of usable nights, less rain, and then the wind speeds. We need to look at seeing. That is the turbulence in the atmosphere. We have some almost like 100 kilometers of turbulences, which people have to look at it. So the turbulence can be because of topography, and then various things play in that. So we need to monitor these for years to see how stable this atmosphere is for night sky astronomy. This is measured by called seeing here. So if you compare with the Mauna Kea, which is one of the most superior in the northern hemisphere, and then maybe Iowa Hanley comes maybe second best or third best. There is another one which is in Canary Islands in the Atlantic Ocean. Mauna Kea is in the Pacific Ocean. So, and the people look at average brightness of the sky, extinctions and things like that, and water vapor, and what are the extreme temperatures. Of course, we require the logistics as well. So all of these things we take into account while selecting these sites. That's why astronomy requires very remote areas, but of course, they're also fascinating. Okay, that's where we are about this now. India's foray into this international participation, which Swati just talked about. Apart from the TMT project, India also is participating or building the large-scale physics or astronomy facilities. For example, Indian Neutron Observatory. That is for various reasons. It's got delayed because of protests at various places. And then ITER, which they want to create a mini sun. ITER is an international thermonuclear experimental reactor, and they wanted to confine the plasma and then produce the energy through fusion rather than fission. So again, is a LIGO. LIGO is what's called LIGO India Gravitational Observatory, which recently you might have also heard, and the recent Nobel Prize also won for detection of these gravitational waves. And then again, which is now being built in Maharashtra. This is both USA and India. And then Square Kilometer Array, which is one of the largest array for the radio and across the two continents, basically. That is South Africa and Australia. Of course, the TMT, this is another 30-meter telescope. India is part of it, which I take a little more time on that participation. So what are the major mega science astronomy projects in the world? These are the three. That is a giant Magellan telescope, which is again Australia and some Americans and then South Koreans. And then 30-meter telescope, which is Swati already said that China, Japan, India, USA, and Canada. And ELT, extremely what's called European extremely large telescope. These are all the European countries together. They are building this telescope, and all of these are expected to be were expected to be operational by 2024 or 25. But then all of them got delayed because of technological issues. And then in the case of TMT, we have the cultural issues on the mountain because the native Hawaiians continue to protest and then stopped the work. So we are working with them and then see how culture and science can coexist. So hopefully we will be soon resume the construction on Mauna Kea. So if you see over the years, you can see the size you can get an idea what is the size of these 30-meter or 39-meter, the new next generation telescopes in the over last 120 years. And then the current 10-meter class telescopes are, these are the Keck telescopes. Swati, can you see the cursor showing here?
Yes, sir.
Yeah,
It is
yeah.
visible.
So these are the two twin Keck telescopes, which are based on, again, segmented emitter. I will come back to on that, what it is. And these are the Gemini North and Gemini South, both the southern hemisphere and one northern hemisphere. And so these are some of the largest telescopes currently we have. And these are the new ones, the big ones, These are giant Magellan telescope. That slightly concepts are different, but then so everybody wanted to do different technologies. Okay. And why these all got delayed now? By this time, we all hope to have this by this in 2023-24 time period. So maybe I think we jumped little early into these things. When I look at empirical data, this I taken one of the books. So from the naked eye before that, and then from Galileo around 2.6 centimeter smaller the mirror, to all the way here. So when I put this one, these all have the current telescopes. If I go with the empirical data, so they should come in somewhere in 2040s, not too early, not in 2020s. Maybe that's what we are into. So all the telescopes got delayed now. So for various reasons, one is they require huge amount of money. Particularly, none of them were built earlier. A lot of technologies we need to work on various technologies to realize them. Of course, TMT is faced with cultural things. It's again a size perspective. This is our largest telescope, DOT, 3.6 meter in the country. This is the VPT, that is our own 2.3 meter telescope. This is one of the Hale 5 meter telescopes, which produced an enormous amount of science, including Hubble constant and things like that. This is the Keck telescope, and recently this the black hole mystery got a Nobel Prize in 2020. This is the Keck telescope, and then this is the TMT currently. So why India needs two? India currently had when we started into this project, and then we had only 2.3 meter telescope. So it's a ATMT 2 at 30 meter. It's a big jump for the country for various reasons. One is the technology capabilities, money, and then greater opportunity. And then we need to have a bigger jump rather than go in a linear way. That would take a long time. So it's a challenging climb for us when we got into. So why do you require larger and larger telescopes? Yes, larger the size of the primary mirror, that aperture, farther distance one can see that you might be knowing. So the flux or photons are directly proportional to the d square, that's the size of the aperture. Larger the size of the primary mirror, also is the greater the resolving power of the two stars close together, things like that. That goes to lambda by d. So lambda is at wavelength, and d is the diameter of the thing. So that's what it is. Of course, if you go further, if it is equipped with adaptive optic system, I will come back in the next thing. And then this power of this larger the telescope goes actually d to the power of 4. The way the photons collected at the airy disk at the center, that becomes almost like 200 times more powerful than an 8 meter class telescope. That is number of photons collect in a given amount of time. Okay, so that's the power it gets into when you go to the size. So the TMT features is of course 14 to 200 times higher the sensitivity, depending on seeing limited. That means just atmosphere is there, and the adaptive optics, somewhere you take care of the atmosphere. That means make the corrections for the presence of the atmosphere, and make it this 30 meter telescope as if it is in the space, based on the technologies. If you do that, and then it goes to d to the power of 4. And then the much better resolution compared to even 8 meter class telescopes. And then it far surpasses by 1,000 times the Hubble telescopes in different ways. Okay. So this is again why we need to have more. You can't make a one single mirror because 30 meters is huge. And the thing is, when you need very accurate images. As stars, the farther away, you need quite accurate. You have to point them. You have to observe them with the long exposures, sometimes few hours. So the entire thing has to be stable. So when you have a large 30 meter one single mirror, And then it has various problems during the night. For temperatures, it can sag, gravities, it sag at different heights. So what is the largest? There is the limits people calculated. It's a closer to 8.2 or 8.3 meter telescope. One can have a single monolithic temperature, but then after that, you need to have a segmented mirrors. So this now 30 meter is a 492 primary mirrors. Each one of them is around 1.45 meters. You have to put them all together as a 30 meter primary. Okay, so what makes this 30 meters so complex is that you have to make these all 492 meters act like a single monolithic mirror, as if it is a single mirror at any point in the sky when you are looking in the sky. Okay, and maintaining the figure from one end to another 30 meter across these 490 meters, 2 nanometer accuracy, surface accuracies. That is a daunting task. You can think of 2 nanometers. Quite. So the complexity from that requirement, everything is the complex. The way you have to make the mechanical systems, the way you have to integrate all the other systems. And it has either side of this perpendicular to the optical axis, you have these all instruments sitting, so huge instruments, different instruments, imaging, spectrographs, adaptive optic systems, things like that. So this is the primary mirror. You can see how the structure is. And then the primary mirror, the light comes from the top, the faraway objects, and then reflected back is a 30 meter from here to here. The secondary is again, it is a 3.6 meter on the top. And then that light comes and reflected by the flat mirror, tertiary mirror. This entire something like, closer to 2 meter, the light beam, entire 2 meter light beam goes into these instruments, big instruments, which is like a room size instruments. So further analysis of the light, which is coming from these celestial objects. Okay, that's what the people do. So, and you can see this is our largest telescope. It sits into the center of this tertiary mirror for the 30 meter telescope. So that is the tertiary mirror. That's talked about passing the light from the primary, secondary. So that's what is the largest. So it's a huge mammoth. Okay, so it's a very high, it's a built-in adaptive optic system it has. I will just go through quickly on those things. So these are the various instruments which are placed for this telescope. Again, this is a secondary tertiary system, which is basically takes the light beam from the secondary and then gives it to various instruments across the platforms. So now you must be wondering where this telescope is going to be situated. It is in the Pacific Ocean in Mauna Kea, an island here. So that's the place which is going to be. Those are the partners. So, and the site looks like this. It's an extraordinary place. It is a dormant volcanic place. And then it is already home to a number of telescopes from Japan, Europe, Americans, because you don't have many places to go for these observations. That's the reason the people choose. These are the places people choose. And this is the place which is going to be the TMT telescope here. It's going to be. So these are the world's largest telescope, the Keck telescopes you might have heard, then Gemini North telescope, and then the Subaru telescope from Japanese. These are the 8 meter class telescopes. And then, so that's the world's largest telescopes now. Whatever the knowledge we have about astronomy, much of this comes from these telescopes now currently. So that's our place. We just talked about adaptive optic systems. You see the space, how empty. So it's totally empty. When you come to the atmosphere, you have large number of particles, and then number of 10 power 19. So all of them give refraction. So it is a differential refractions. For example, these light waves which are coming from the space, they're almost like a plane waves. But once they enter into the atmospheres, now you see that the degraded and the distorted wavefronts. So now, sitting telescope on Earth, how to take this distortion that comes into the adaptive optic systems. Okay, and all of these particles there, they move in 5 to 10 milliseconds, some of them. So because of that, you see these, when you are looking at the night sky, the stars twinkle quite a bit. That twinkle is because of the distortions, caused by the atmosphere. Because the atmosphere, when the light goes through the atmosphere, it goes through different layers, having different temperatures. The refractive index constantly keep changing. So now you get these the images at different places, So that's what it happens. So we don't want these things. That's a basic thing is. So for that, there are, it's called adaptive optic system. We create, either we can have a reference star closer to the science object, or we create a star just above the atmosphere by using a laser guides. And then based on that, the light which comes from the primary mirror, we send it to the deformable mirror, and then that deformable mirror takes the analyzed wavefront, the distortions, it models. There's a wavefront sensor. That wavefront sensor takes that, the incoming wavefront, it analyzes it. Oh, these are the distortions. So now you give the opposite effect by using the deformable mirrors, which are constantly moving, so the wavefront changes, and then it goes into the camera. So that is the basic principle it works on, corrections on real-time basis. So the incoming perturbed wavefront, it comes. So you see, then we have the deformable mirror, but deformable takes from all the analysis from the wavefront sensors, and then which applies it, and then you can get almost like a plane waves, and then which you can see much better amount of photons, concentrated photons. So that's if you uncorrect it, just seeing limited, that means atmospheric limited. That's the way image you can see. But the same image, if you look at if you look at through adaptive optics closed system, and then those are actually made up of two. So that is a huge amount of information you got. So to understanding various other issues related to celestial phenomena. So otherwise you don't know, you are completely blind. Oh, this is a very big blob there, what we are looking at it. So that's the difference it makes, adaptive optics versus without adaptive optics. You can see the left one without adaptive axis. With adaptive, actually it was a galaxy, and it is a spiral galaxy. The center is the core, So yeah, so okay. So that's about 30-meter telescope. Why people wanted to do, and few science cases, of course, because of these good angular size and sensitivity. So we have a lot of projections for this in the next century, what the TMT is going to do, understand many known unknowns, which we can predict what we wanted to know. But of course, there are many things which we don't know, what we know, and that is very difficult to predict. That will come as and when you start looking at these telescopes and analyzing the data. Prediction is very difficult, but especially if it is true, if it is about the future. So needs hope. So one is our solar system itself. You need to have really high resolution to understand the surfaces of various moons of our own planets. That will be possible with these telescopes. And of course, what kind of near Earth objects, the smaller things, which you want to really track them, and then you need to have very special resolution, the tools in our hand. So that will be done with these things. And of course, are we alone in the universe? So a few years ago, around 25 years ago now, we came to know that we don't know there are people, but then we know that there are solar systems like ours, our own. So that itself is the now new thing. And now which we have some thousands of the new planets were discovered around various other stars in the universe. And that's an extraordinary. Now, people wanted to know, so what kind of these planets? Is there water in those planets? Is there life in those planets? These are the very important fundamental questions, and hopefully hopefully people solve in this century with these all big telescopes. Okay, and so that's where how our own planets form, and then what things are there. So these are very important issues which are going to be addressed. And of course, there are various other phenomena. So normally now we have access to our own galaxy, particularly in a detailed way, chemical history. If you want to know chemical history, you want to have a spectra. If you want to have a spectra, it is not like a single image, because spectra is millions of images. Because we need to split the light into uh, hundreds or thousands of lines. And then to understand what it represents each line. Each line represents some iron of different excitation potentials, different transitions, lithium, europium, and things like that. That requires a large amount of light. That means you need to have a large photon collecting bucket. That's why you go for larger and larger telescopes. So now you want to see what kind of chemistry the other galaxies have. Now we know what kind of the chemistry, at least certain extent, with the existing telescopes. So we can go only some level. So people wanted to do more and more. So that's what, if you know little and then you want to know more and more, that's what it all comes into. So, okay, this is some of these things, and I recently got a Nobel Prize in 2020, Andrea Ghez and Reinhard Genzel. Andrea Ghez was our one of the science team for the TMT project. And then she got this for her real efforts of more than 15 years, mapping the stars in the center of the galaxy. Each was a point, taking the position. So now you filled up those, the orbits. All these orbits have a one common center somewhere here, depending on their masses. So that's where they got. There is a massive black hole in the center of the galaxy. Okay, this is a direct evidence. This was done using Keck and VLT telescopes, 8-meter class telescopes. This just to give a snapshot of it. This is a spectra looks like. What are our first stars look like? Because these are all within our galaxy. So when the universe evolves, and then you form stars, you form galaxies, and things like that. And then when the stars forms, the stars die, and then with the new material, because stars are the one they produce various elements because of the high temperatures and high densities. They produce a number of elements, starting from, of course, the hydrogen is the primary element there. Then from there onwards, helium gets produced, carbon gets produced, lithium gets produced, all of these things, And then when you go backward into the beginning of the universe, as you go backward and backward, you see less and less number of lines, here, because it is an enrichment of the universe with the chemistry. When you go to a few billion years ago, there was less metals and less elements. You can see the last one here. I can show you. There's no lines at all. Very few lines here. The strongest line is the higher one, and you see here. And it's now one of the oldest, what's called oldest stars. The first stars. One of those first stars in the universe, which has very, very less metals. It is almost like, more than 10 million times less than what we have in the sun. That's an amazing, okay? And of course, people work on various nucleations, the europium, and how these heavier elements gets produced in the stars, and based on their different metallicities, different elements relative to each other, and then people come to understand what kind of nucleosynthesis is really operating in the stars, how they are expelled into the ISM. That's what people do. Yeah, of course, this was the previous one, I think 2018, got a Nobel Prize for this expanding universe. This is again based on observations, came from Keck about monitoring of the supernovae, further and further how the universe is expanding. As you go further and further, and then, people found there is a signature for expanding universe rather than constantly expanding it. So what is driving it? So one of them driving is the dark energy, which we don't know what the energy is, which is driving it. What we know is very little based on visible visible matter, that just close to 4%. But the rest of the things we don't know. There is a significant amount of dark matter, which is held up in black holes and things like that, which you can't see, which is only indirectly we can see by looking at bending of lights and things like that. So, of course, exoplanets, I think this century is going to be really hunting for these signatures for harboring life and things like that, understanding spectra of those planets and things like that. Currently, it is not possible because the planets are, they don't emit light, but only they reflect very feeble amount of light. So how to get that light? So that reflected light has a signature of the atmospheres, like our own Earth. Okay. So people do. So quickly, in the 5 minutes, I just ran through India's contributions to the project. Since you are all engineering students, you may be interested in this. We do quite a bit of things, because government of India said we don't want to pay too much cash to the project, but much of our participation should be in providing, developing our own systems, use our own industry and then technology and things like that. And we do part of, polishing those percent, some number of segment polishing, which itself is not trivial, it's completely non-trivial. And then every country wanted that, want to have some share. So China doing some part, we are doing some part, US is doing part, Japan is doing part. And then the entire M1 control system is our system, which is a very critical area, because all these mirror 492 segments have to be controlled very precisely throughout the night, year after year, and maintaining that the entire mirror surface as like a single mirror, though it is a 492 segments. So that's a very critical. So now you have actuators, sensors, and electronics. What the sensors will do is, these all 492 segments are separated by 2 mm from each other. So what happens is, because of temperatures and because of where the telescope is there, and then they do move from one another. There is a differential movement at the micron levels, sub-micron levels. And then the sensors are attached to each segment. These 492 segments are there. Each segment will have some 6 sensors. These are all hexagonal. At each side, you have a sensors. The sensors will send something, and then that will feed into the system. Then the actuators, each has 3 actuators, and then they make that particular mirror. Oh, you are out of the sync from the predicted, from the reference frame. So you have to move a little bit up. So that is real time, So that's what they do. And then the entire segment support assembly, it is up to a mechanical system. We are doing it, and then mirror coating also we are doing. A lot of software is being developed in India, various companies. There are more than 24 companies are involved, including Godrej, L&Ts, and then ThoughtWorks, and then people like that, So these are the various systems we are developing. We need for each mirror the segment support assembly, number of actuators required, thousands of sensors we require, and then this mirror polishing also we are doing. So for this, we now created a state-of-the-art facility at the Indian Institute of Astrophysics. There is another campus we have is called CREST, which is a 40-acre facility. For this whole purpose, in India, we don't have large optics facility in the country anywhere. And this is going to be the first facility. Currently, ISRO does up to 1.2 meter kind of mirrors. They do take a year to 18 months to polish one. And then the goal is we need to have a 1 mirror every 2 weeks. That's a goal. That's unprecedented. So that's the reason everybody wanted to have these mirror technology developed or taken from one of the guys we made earlier for Keck telescopes. So these mirrors came to this facility now as a Japan's in-kind contributions. These are zero dur, that means zero expansion mirrors, which we have now stored there. So things are getting delayed because of this pandemic. That's the way it looks like. All 492 segments are put together. So, and these are the framework for it. And again, these mirrors are quite off-axis, and then every one of them is aspheric. Making this aspheric is extremely difficult. This asphericity from center to the edge, it changes quite a bit, few microns to almost 28 microns. So that's an extraordinary, because you want to keep light from each mirror at a single focused point without any errors. If that is an extraordinary, you need to require that. So that's where it gets into, done. So you have to maintain this entire thing less than 2 nanometers surface area. So these are completely new technologies making these mirrors. That's what we are into now, getting these technologies, because this is very fast. It's not like in earlier the small tools, but you need to take quite a bit of material removal, a quicker way with the large tools.
Professor, are you here? Participants, I think Professor Reddy have a connectivity issue at his end. He'll join in a minute. Please bear with us.
Swati, I don't know where I lost my.
Sir, you just lost your connectivity, sir. Would you like to share your screen again?
This is the same screen, or is this the screen?
Sir, we are not able to see the screen yet.
Oh, I need to share again. Okay,
Yes.
sorry. Okay, sorry. Can you see the screen?
Yes, sir.
Okay. So
the previous
you
screen, the previous slide.
Okay. Yeah. So these are the technologies, which is a large tool policing, which is called stress mirror policing. That basically people do with the moments, they bend the mirror and then do the spherical policing and then reverse it so that you can get required shape. So these are completely new. So these are the ones which we are getting from one of the industry called Coherent. Our engineers are there, and then it is through TMT project, because the same people are doing for them too. So the large number of the systems we are developing, actuator systems, sensor, various companies in India, and these are being tested at JPL. So some of these things are being tested for lifetime tests, because they had to go through accelerated testing process, so whether the design works or not. So, and this telescope has to be nominal operation is 20 years, by then it should go at least 50 years. So these are some of these things. Our own engineers went there in JPL looking at assembly of process. And this is one system. We need to have 492 systems, something that is put together and make as a single system for this. So a lot of mechanical systems are happening across the country. Of course, we had a problem when we were start constructing. You can see when we are on the in Mauna Kea, on the top of the Mauna Kea summit, and these are the representatives from various countries. And I was accompanied by the ambassador, honorable ambassador for Indian ambassador for United States, Saranjit Singh Sahu. So, and these are various partners representatives. And these are the protesters. They came and then their protest is the mountain is sacred for them because of their ancestors live on them. after they passed away, and then we should not desecrate it. And that's what their contention. But then we don't know how to manage, but we are working with them. So the project is delayed as construction now, but a lot of technical work is happening across the partnership. Meanwhile, and then we also chose an alternative site for the TMT project, which is in La Palma, Canary Islands, which is a very similar site, but not this site as dry as this site, but that is in Atlantic Ocean. So that also has a couple of bigger telescopes there. That's where we are in the fight, culture versus science issues. And hopefully we all understand. So yeah, we are working with Native Hawaiians and understanding their sensitivities, what needs to be done to take care of their issues. At the same time, having this telescope. So that's about the telescope. And then my own research, which I didn't touch upon, and then maybe I'll just give you a glimpse of it very quickly. What is the lithium problem? Is a cosmic lithium problem. You know what happens is the models give you, and then some of the experiments provide you. And during the Big Bang nucleosynthesis, lithium has been produced some amount, whatever this amount is called, which is basically 2.67 in logarithmic scale, some amount. That's the Big Bang nucleosynthesis models, which are one of the best models, taking experimental values, baryon to proton ratios, like various experiments, Planck experiments. Of course, observations also provide some number which is much less than what is in the Big Bang, that is 2.2. So there is a discrepancy. That's a lithium problem. That's not our issue. Our issue is to understand how the lithium evolved from the Big Bang, or whatever the primordial value, that's called primordial value, to the current value. The current value, what is seen in the ISM, interstellar medium now, or in very young stars, is 4 to 10 times more than what is seen either in the Big Bang or in the observed primordial value in the stars. So what is that? Where is this increasing is coming? That's what people wanted to know. And one of them is, not the only one of them is in stars, because stars can produce lithium, that's true, but then the lithium cannot stay in the stars because lithium gets destroyed very quickly, because at around a couple of million degrees, lithium gets destroyed. You can see by capturing proton 4Ha and 4He, the helium, which goes back. And then for the seed nuclei is almost like a beryllium. Beryllium is also quite volatile. It gets destroyed to 4He. So it has to escape these internal mechanisms, and then somehow lithium has to come to the surface. And then these stars have a huge convections, and then so the best models predict, some of the sophisticated models, you should not see lithium in the surface of the stars, the period. So the thing is, the lithium, whatever is produced in the Big Bang models, it has to be only destroyed, or whatever it is produced at the time of the birth of the stars from the ISM, it should be destroyed rather than seeing any more extra. That's what it is of models. Exactly, observations also tell you, what I showed you here is observations. I can show you here. This is the star's luminosity, okay? V minus Y is basically some temperature indicator. You can see the stars. Much of the stellar evolution is represented in a diagram like this, luminosity versus temperature. As star evolve, like our own sun, as it evolves, it becomes brighter, but again cooler and cooler. As you go on this, our sun somewhere here, and it goes, become bigger and bigger, 10 times, 100 times bigger. It becomes red, cooler, something like that. While doing is bigger and cooler, and also it has a large convection from the center to the top. So it can bring up the material up, and then the top material goes down. So the lithium, whatever is there in the surface during the main sequence time, as stars evolve, in their life, they get destroyed. So you don't see, as for the theory, physics is concerned. Also, you don't see because of large amount of observations. So there is the theory is correct. Observations are also correct, because observations show that no lithium, you see, as you're coming like this, the lithium is coming down like crazy. So you can see here, this is the way the stars born with this lithium. And now you see how they're getting destroyed. You can see this leftwards, the lithium is coming down in the logarithmic scale. You see it is coming down. Then suddenly it comes down even further, You see almost very little or nil by 100 to even 1,000 times less than, depending on the initial lithium, which is maximum is ISM lithium. That's the way the stars born if they are very young stars. Okay, so lithium gets destroyed. But it's always you get into the outlier. What is the outlier? There was one outlier some 40 years ago discovered, one star which is highly evolved, which showed a large amount of lithium. That's an outlier. You see the huge amount of lithium lying. That's the way the atoms gets absorbed here. So huge amount of, you don't see the similar thing. Exactly the same temperature, same luminosity, same brightness, same age. You don't see line, but you see this line. Why? Why the lithium is seen in very, very few stars? So this came into the picture, and then serendipitous discoveries were made, very few. But that time I had a student here at Indian Institute of Astrophysics. We worked on this problem, and that was in 2009 and 11. So we thought of having a large number, systematic observations of these stars and the lithium. So what we found was all these stars are at particular evolution phase. You can see the particular evolution phase. This is a very specific evolution phase at certain luminosity, at certain temperature. They are all high. You can look at the other right side diagram. These are all actually normal. These are all following the normal theory, but these are not following the top one. Suddenly at particular luminosity, brightness, these stars are a high amount of lithium. There is something is happening there. So the number of papers came on these, hundreds of papers came to understand both theory and observations. So this is not the end, because separating these stars at different evolutions is extremely difficult, because there are a lot of errors in temperatures and gravities. So that's one we wanted to solve this problem. And the solving problem came into the Kepler space mission, which could observe, detect stellar oscillations. Stellar oscillations in the sense the variation in light, and that has a signatures. Signatures from the central core. The central core is so dense, and then it releases some gravity waves. Because of the gravity waves, there is a tiny amount of modulations in the star's atmosphere. These space telescopes could detect those things. Okay. So if you can plot light curve and then deduce certain parameters, you can understand those. And then we know, depending on what kind of density stars has at the core, now we came to know these are all stars are central helium core burning stars, not all the stars which are on these. Only the particular phase which are coming from the top to the red place. The red ones are not on the blue one. Blue one are first time going up, evolving up. They come from there to here. There's an issue. They cannot go beyond that, because there is going to be the huge flash in the central core. It busts. Because of the busting, and the stars fall there. Okay, during that small period, and then you are producing lithium. This was one of the things we published. And then the further discovery came in our Nature Astronomy in 2020 was, we demonstrated that lithium is not being produced while stars are evolving. This is a phase called red giant branch, while ascending this branch for the first time all the way up here, but it is getting produced somewhere here in the helium flash. After that helium flash in the central core, that busting of the helium core, and then stars end up here, this magenta color, these are all in lithium rich. So that means among these stars called red clump stars, in which the core helium is a burning core helium. But the other RGB, the core is a helium inert core. So the helium core is not burning, it is just inert. But here, the core, the helium is burning in the center. So only those stars have. So in between is what is happening between helium core burning and helium not core burning. That's the place is something called helium flash. So that looks like the process, something is triggering the lithium suddenly going up by 1,000 times more than what you see the normal way. That's what I was discovering was there. And then recently, when the paper came, we now localized where it is coming. So looks like after the tip of the RGB, this is called tip of the RGB, okay? Because after that, this phase ends and then starts ending to different age, a different phase of the evolution. So looks like after that tip of the RGB within 40 million years, something is happening. The lithium is getting produced. Because when you looked at it, all these 1,000 times more than whatever you see, this is called super lithium rich. That is more than what you see in the ISM. That means they have to be synthesized. And how long these stars, that phase ends. Based on that, we got statistical information and then put the limit 40 million years, but more likely within 2 million years, this is happening because this is the core helium flash is happening. From here to here, the stars spend just 2 million years. So during that 2 million years, the lithium is getting produced. And then after that, lithium is again depleting back to its original values. So it is a one kind of transitional process which is happening. So this is towards the RGB I just showed you for the sun. And then this is the one which is a inert helium core at the center. But then after that, these stars evolve. And this is one of the major finding also, because it's the first time we saw the evolution of the central core, the degenerate core becoming a convective core through a called gravity period spacings from Kepler space data. I think that's what I try to say to you all, and hope you got some interest in astronomy by this. Thank you very much for this opportunity given by your conference team. Physics for whatever it's called. Yeah. Aspiration.
Fascination to aspiration, Professor. Thank you very much for your informative presentation. Sir, can we take up the questions?
Yeah, please.
Yes. Mr. Shukdev Pandey, please ask your questions.
Hello.
Mr. Shukdev Pandey, I think you have unmuted, right? We can't hear you, Mr. Shukdev. Okay, maybe you can post your question in the group, in the chat.
Yeah.
No, I think he's here. Are you here?
Am I audible? Hello.
Yeah, you're audible. Please proceed.
Good afternoon, sir. Thank you for this really informative session. I have 3 questions for you. Maybe I should ask one after the other. So my first.
Please go ahead.
So my first question is about this. I'm not sure if I'm using the right terms.
Your voice is too low.
I see, sir. How is it now? Is it now? Is my voice better now, sir?
Oh, now it's much better, much better.
I see. Okay. All right. It was about the mic. Yeah. So I have 3 questions. I'll add the first question is about corrective reflection. You talked about some reflection surfaces in the adaptive optics, which were used to correct, remove the atmospheric disturbances. So I wanted to ask whether do they have like tunable morphology? Is there anything like like how is the surface? Can you elaborate on the surface? And the previous presentation was actually about these magnetic nanofluids, and they talked about using magnetic field to change maybe the surface or something. Any connection there?
Yeah, I don't know the latter question, but then see, when planar waves go through the atmosphere is made up of many layers. It has different temperatures. You know that a fractal index changes with the temperatures, and because of that, you see the light gets reflected because of that small particles in the atmospheres, nanolayer.
Right.
That's exactly the reason you see stars twinkling, moving
Yes.
one to another one, twinkling stars, Basically, you don't want that. So when the
Mhm.
planar waves comes, it has a, distorted images. Say you
Mhm.
can take a 2 or 3 distortions. Now what we do that 2 or 3 distortions, there is a wavefront sensor. That wavefront sensor takes that distortions and then
Mhm.
passes it to smaller deformable mirrors, which with very thin deformable mirrors, the array of
Right.
deformable mirrors. This pattern goes there, and then the deformable mirrors acts in opposite direction for the incoming
Yes, sir. So sorry to
incoming
interrupt
distorted
you.
wave.
I understand that
Yeah.
process. My question was about those deformative mirrors. How do we deform the surface? How do we deform the mirror?
Oh, you just move up and down.
Oh, I see. Okay.
Yeah.
Okay.
These are the
Okay.
very small ones. They just,
Okay. All right.
it is similar to the all segments, So,
I see. I was imagining that maybe the surface is being changed
oh, no, no,
by
no.
some way. Okay.
No, no,
All
no, no,
right.
no, 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 no.
Okay.
Sorry,
All right.
sorry.
So my second question is about, like, on one side we have these adaptive optics where we try to remove the negative effects of atmosphere, and then on the other side we have another option of maybe using satellite mounted or space station mounted telescopes. Of course, the scale is totally different. Like, we have a huge
Yeah.
limitation on size and weight. But, like, what are your
Yes.
comments?
Yeah, that's true. Now, the space is the best one. But the thing is, for example, now there is one telescope which is going to go up by December. That is James Webb Telescope, which is 6.5 meter. It is a next version of the Hubble Space Telescope, and
Right.
which also now got delayed more than 25 years. And then they spent close to $10 billion now. And putting that class of telescopes in the space is very, very expensive.
I see.
Very, very
Right.
expensive.
Right.
And
Yeah.
now, given these technologies, now the both software and then various material technologies available, and then people can do using adaptive optics. You can get rid of this atmosphere. Basically, that's what I'm trying to say.
Right. So my last question is about, like just that the atmosphere has got like these negative effects. Like, is there any kind of eclipsing effect happening from other stars and planets which are in between the star that is being observed? And, like, how do we differentiate between planets and stars? Like, if they are in between our observation.
Yeah, you know the planets and the other things. Certainly, it's easy. But then what we don't know is near Earth objects which are zooming, like a comets and asteroids, because you see in the frame, huge streaks, because they're moving faster. Closer the one
Right.
moves faster. And then if you want to take a quasars, which is billions of kilometers away, and which won't move, that one. And
Yes.
then another major problem for astronomy faces is because number of satellites in the space. Now the number of is increasing quite a bit. So that's going to be also a mess. It's going to create something. So
I see.
yeah,
I see.
that's going to be a problem. So now basically people have to move to the moon to have your own telescopes to study
Right.
the universe. So
All right. Yes. Thank you so much, sir.
yeah. And then I see there are some questions on this. What is the mirror made up of? It's a glass material, and so it is the thermal expansion is close to zero, and it is not a metal. Metal, you cannot achieve that. And these are coming from Wahara, Japan, and it is their in-kind contributions, and they are sending to us blanks they make. Like a huge furnaces they have. So, yeah.
There's a question from Mr. Libert. On what wavelength range we could observe
Yeah.
the interstellar medium?
Yeah. So the interstellar medium can be done in many different ways, So one is the radio waves you can do, and depending on, sometimes this interstellar medium also the glows because there are stars within those, the medium. So yeah, you can do the optical. For example, the starlight, if you glow back the background of it, if the interstellar medium is the front side, so that light goes to the interstellar medium, and then interstellar medium, either it emits or absorbs depending on the temperatures of the stars, and then you can understand the composition of the interstellar medium as well. So interstellar medium itself, of course, there are radio waves and things like that. So particularly infrared things. So people do that infrared too, because many stars are, protostars, which are hiding behind these huge amount of dust. So yeah, it is like, a small kid going around the elephant, which is a tail, which is a mouth. So you need to have all these tools to understand the universe as an elephant. So you need to have all these tools of all entire electromagnetic spectrum to see the entire phenomena, X-rays, visible, and things like that.
That's a good analogy, sir. Mushiban Anande wants to know, what is your view on parallel universe and multiverse? And also, there is a follow-up question by Mr. Mubarak Hussain. Is there any experimental proof on multiverse?
Yeah, I don't think that there is a multiverse, any experimental proof currently. I think we are still grappling with our own universe first. So we have to see what the multiverse is about. How do you get a multiverse? That's another thing. Yeah. So I'm sure there must be there. You can always conjecture that, because when people are there, on Earth, now people are looking at it, why we are so special. There are so many stars in our own galaxy itself, more than 2 billion stars. There are now so many planets around these stars, which ourselves are discovering. And why are you so special? Maybe 1 in 100, maybe 1 in 1,000 planets must be, has similar conditions like us. There's a probability always. So similarly, why this universe so special? Why one Big Bang? There may be many Big Bangs, parallel universe. You are right. These are the questions which, of course, we all need to do. Think over and understanding it, what requires to probe these issues. So,
Okay, thank you, sir. I have a question, sir. So
Please,
you,
Swati.
yes, sir. You had shown that many telescope projects India is involved with. Like you told that there is a considerable delay in 30-meter telescope or INO project because there are some local issue with the people living there. So how do you
Yeah.
think? What do you think as an effective way to make people understand why these projects are essential? How to take science to them, the positive
Yeah,
side?
see, I don't know much the politics around INO, Indian Neutron Observatory. Already 10 years got delayed. And I think it is now close to Madurai. It is, because again, they wanted, yeah, so it's underneath the mountain, they are doing it. And then I heard various newspapers there on the mountain is a small temple or something. And also the people now misunderstood completely these neutrons are really harmful, though how to make them, this is every day you are bombarded with number of neutrons, they're going through your body in millions. It's very difficult. They all look at, these are all multinational people or whatever. So they gives radiative effect. I think what the requirement is now within the country, reaching out to the public in a much more serious way. All these institutes now, I think, getting up towards that, writing articles in various newspapers. What is the science? What is harmful? What is not harmful? And this is all about knowing things about various things. It's for all for better living, better understanding. So it's basically outreaching plus understanding their own issues and then see what is the best way to do. Yeah, it's not only that in India, but then the similar sentiments in Hawaii. We heard all kind of negative theories, because we send these laser guided, if you want to create an artificial star for reference frame, that goes into 100 kilometers, the laser guide. They thought that is all, the military purpose. And if some war comes and then that becomes a central point for them. So all kinds of misinformations, And then, of course, there is a misinformation is about, not misinformation, it's their own belief that their ancestors live us in the mountain. So these are the issue which we don't know how to tackle, but then we are trying to understand. A lot of effort is going on there. The people on the ground, the More Foundation, they are putting a lot of money into this project, almost like they put $200 million, and our own is around $200 million. This project is now, the initial cost was around 1.45. So now it is reaching almost $3 billion. So, yeah. So it's a cultural aspect, is a serious aspect is coming into the play. Any remote places, you have these indigenous people and is very sensitive, both for political and for various purposes.
Okay, sir. So, thank you. We'll take one last question from Ardra KP. Let me unmute you.
Hello, sir. Can you hear
madam.
me?
Yes, yes.
Sir, can I ask a question about cosmology?
Yeah, any question, whatever, if I know.
Yeah, sir. A few years ago, famous scientist called Alan Guth introduced a theory called inflammation in cosmology, right? So
Yeah.
at that time of the prediction, it was one of the successful theories. But after that, many contradictions came because many people like talked against the theory. So do you think in future are we able to predict some more good theory that can talk about the expansion of the universe and how it is going to be like that?
Yeah, man, now more than the theory is the based on the current physics, what we know, and built on that. But then now you have large number of tools are coming, like the large scale telescopes and things like different experiments. For example, this accelerating universe came from observations by observing faraway stars at different epochs, and then as you moving farther and farther, and things are going faster and faster. So that's an expanding universe. So we have now proper experiments there. So there was a beginning, and there is that's known, and then our universe is expanding. That is also known, but it's not expanding in a constant way. But after some period, it is accelerating. What is creating this acceleration? What is pushing that to the acceleration process? We don't know. Is a multi-universes problem, or there is something else, or so yeah. So now much of the theory will go away, whatever certain theories, but some theory will be what's called verified. So all right. So it's all about now larger experiments, observations. So that's why the astronomy becomes quite expensive business. So yeah, we can't have this in the lab. So all the time you have to go in the field and then get these things done.
Thank you, Professor.
Thank you. Thank you very much. Yeah, the space debris do affect quite a bit of these things. Yeah, this is one area now. I think the entire astronomy community is looking at it, how to do this one. So, of course, we don't have any control over it because these are all economy. So, yeah, I think that needs to be addressed, because now Elon Musk is putting some thousands of them, and India is also going to put thousands of them, because if you want to have a internet everywhere on Earth, and then you need to have these number of satellites, So then, yeah, that is going to affect some of these astronomy things.
Thank you for answering the questions, Professor. You have familiarized the participants with the past, present, and future telescope projects that our country has been involved with. And also you have beautifully projected the questions that drive high-end research like dark matter, exoplanets, and your work on lithium was also very monumental. I can see that so much effort has gone in cleaning up this information and beautifully making it as a presentation to apprise the participants of the advanced research going in astrophysics. Thank you very much, Professor, for your effort and time.
Thank you, Swati. Thank you, everyone, for having me here, and then enjoy. And then if you do require anything, and then let us know, IAA, and then they have a lot of what's called training engineers. Even TMT has the training engineers. They have, internships in astronomy, PhDs. We have these engineering PhDs called, people come as a PhD students, and then they can take MTech and then go away, or they can continue in astronomy PhD. That's called MTech, integrated MTech PhD program. So thank you very much all.
Thank you for that information, sir. Thank you.
Bye.
Could you please stop the sharing, sir? Thank you.
Thank you. Thank you all.
Yes. Our session 3 concludes with this lecture. I once again thank all the speakers of this session for their wonderful presentation, and also the participants who have been very keen to listen, learn, and interact with our dignitaries. We have one more session that would be led by Dr. Jane Gregory, University of Cambridge at 2 p.m. before we could culminate the symposium. Dr. Gregory is going to speak on science communication, and this is rather a common topic to students from all disciplines. An undeniable fact is that communication works for those who work on it. So I encourage the participants to make wise use of this session where Dr. Gregory will help us to tone up our communication skills. This is Swati Shaktivel, President of NITT Optica Student Chapter signing off. Have a good day and meet you all back at 2 p.m. Thank you.